Hello and welcome. I'm so glad you're here with me tonight. Find a comfortable position wherever you are. Let your shoulders drop, release any tension you might be holding in your jaw, and take a slow, deep breath. Hold it for just a moment, then now let it go. Tonight we're going on a journey together, a peaceful exploration into one of the most beautiful and fundamental concepts in all of mathematics. We're going to discover how polynomials, these elegant mathematical expressions, are woven into the very fabric of our universe. But don't worry if mathematics hasn't always been your favorite subject. Tonight there are no tests, no pressure, no rushing. We're simply going to wander through ideas together, at a pace that feels calm and natural. Think of this time as a gift you're giving yourself, a chance to let your mind drift through the cosmos of mathematical thought, to see patterns and connections that have been hiding in plain sight all along. The territories we have wandered through have led us here, to a place where the exponential function reveals something about the nature of knowing itself. We have traced its appearances in growth and decay, in the complex plane where rotation and magnitude intertwine, in differential equations that model how the world changes. Now we turn toward questions that feel almost philosophical, though they remain grounded in the precise language of mathematics. What does it mean to understand a function completely, and how does the exponential illuminate the boundaries of that understanding? There is something peculiar about e raised to x that separates it from almost every other function we encounter. It is its own derivative. This single property, seemingly simple to state, cascades into consequences that ripple through every branch of mathematics. When you differentiate most functions, you get something different. The derivative of x squared is 2 times x. The derivative of sine of x is cosine of x. The function changes under the operation of differentiation, but e raised to x remains itself, unchanged, eternal, in a mathematical sense. This self-similarity under differentiation connects to something deeper about exponentials. They represent the purest form of proportional change. When a quantity grows at a rate proportional to its current size, the function describing that quantity is exponential. Bacteria dividing, compound interest accumulating, radioactive atoms decaying, all follow this pattern, because the mechanism of change depends on what currently exists. Think about what this means for a moment. In a colony of bacteria, each bacterium can divide. The more bacteria there are, the more divisions occur per unit time. The rate of growth is proportional to the population. This gives rise to exponential growth, not because we chose exponentials arbitrarily, but because they are the mathematical expression of a process where present state determines rate of change. The natural logarithm, the inverse of the exponential, reverses this relationship. Where e raised to x converts addition into multiplication, taking any sum and transforming it into a product, the logarithm converts multiplication into addition. These twin operations, exponentiation and logarithm, form a bridge between the additive and multiplicative structures of numbers. Historically, this bridge had enormous practical significance. Before electronic calculators, multiplying large numbers was tedious and error-prone, but adding them was straightforward. Logarithm tables allowed you to convert a multiplication problem into an addition problem. You would look up the logarithms of the numbers you wanted to multiply, add those logarithms together, then use the table in reverse to find the number whose logarithm equaled your sum. That number was your product. This technique, developed in the early 17th century, revolutionized computation. Astronomical calculations, navigation, engineering, all benefited from the ability to replace difficult multiplications with simpler additions. The slide rule, the calculating device used by engineers and scientists for centuries, is essentially a physical implementation of logarithmic addition. But beyond practical utility, the logarithm reveals something about how numbers are structured. The multiplicative properties of positive real numbers mirror the additive properties of all real numbers, and the logarithm is the function that makes this mirror visible. Under addition, the real numbers form what mathematicians call a group. There is an identity element, 0, which when added to any number leaves it unchanged. Every number has an inverse under addition. It's negative, which when added returns you to 0. The operation is associative, meaning you can group additions however you like without changing the result. The positive real numbers under multiplication also form a group. The identity is 1 since multiplying by 1 leaves any number unchanged. Every positive number has a multiplicative inverse. It's reciprocal, which when multiplied returns you to 1. Multiplication is also associative. These two groups are isomorphic, meaning they have the same structure despite being different operations on different sets. The logarithm is the isomorphism, the function that maps one group onto the other while preserving the structure. The logarithm of a product equals the sum of the logarithms. The logarithm of a quotient equals the difference of the logarithms. The logarithm of e equals 0. The logarithm of e equals 1. This perspective, viewing functions as structure-preserving maps between mathematical objects, is central to modern algebra. The exponential and logarithm are early examples of this viewpoint, discovered long before the abstract theory was developed. They showed mathematicians that seemingly different parts of mathematics could be connected by finding the right transformations between them. Now, consider what happens when we extend the exponential to complex numbers. This extension is not arbitrary. It follows necessarily from requiring that the fundamental properties of the exponential be preserved. We want the derivative of e raised to z to equal e raised to z, even when z is complex. We want e raised to the sum of two complex numbers to equal the product of their exponentials. These requirements determine the function uniquely. The result is one of the most beautiful formulas in mathematics. When you raise e to an imaginary number, specifically I times theta where theta is a real number, you get the cosine of theta plus I times the sine of theta. The exponential of a purely imaginary number traces out the unit circle in the complex plane. As theta increases from 0 through 2 pi, the point e raised to I theta starts at 1, moves counterclockwise around the circle, passing through I at a quarter turn, through -1 at half turn, through -I at 3/4, and returning to 1 after a full rotation. This connection between exponentials and circular motion is not coincidental. Both arise from the same differential equation. The defining property of sine and cosine is that their second derivatives equal their negatives. The second derivative of sine of theta is negative sine of theta. The second derivative of cosine of theta is negative cosine of theta. This differential equation describes oscillation, the back-and-forth motion of pendulums and springs and waves. The exponential function satisfies a different but related equation. Its derivative equals itself. But when you combine exponentials with imaginary numbers, you get solutions to the oscillation equation. The function e raised to I theta satisfies the condition that its second derivative with respect to theta equals -1 times itself. This is exactly what we need for oscillatory behavior. So exponentials unify growth and oscillation, two phenomena that seem completely different physically. Growing populations and swinging pendulums are described by the same mathematical machinery. The difference lies only in whether the exponent is real or imaginary. Real exponents give growth or decay. Imaginary exponents give rotation. Complex exponents give spirals, combinations of growth and rotation simultaneously. This unification is not merely elegant, it is practically essential. Electrical engineers work with alternating currents that oscillate sinusoidally. Rather than tracking sines and cosines separately, they use complex exponentials, treating the voltage or current as the real part of a complex quantity, whose imaginary exponent increases with time. This simplifies calculations enormously, turning differential equations into algebraic ones. The same technique appears in quantum mechanics. Wave functions that describe particles are complex valued. Their time evolution involves exponentials with imaginary exponents related to energy. The probability of finding a particle at a given location is the square of the magnitude of the wave function. The phase, the angle in the complex plane, determines interference patterns when waves combine. We have spoken of Fourier analysis before, how any periodic function can be written as a sum of sines and cosines, or equivalently, as a sum of complex exponentials with integer frequencies. This decomposition is fundamental to signal processing, to acoustics, to any field where waves play a role. The exponential function is the natural basis for these decompositions, the atomic building block, from which all periodic behavior is constructed. Consider a musical note. When you pluck a guitar string, it vibrates at many frequencies simultaneously. The fundamental frequency determines the pitch you hear, but the overtones, the higher frequencies at integer multiples of the fundamental, determine the timbre, the distinctive quality that lets you tell a guitar from a piano, even when they play the same note. Fourier analysis separates these frequencies, revealing the hidden structure in the sound. Mathematically, this is saying that the complex exponentials form an orthonormal basis for the space of square integrable periodic functions. Orthonormal means that different exponentials are perpendicular, in a sense defined by integration, and each exponential has unit length. Basis means that every function in the space can be uniquely written as a sum of these exponentials. The coefficients in this sum are the Fourier coefficients. To find them, you integrate the function multiplied by the conjugate of each exponential. The orthogonality ensures that only the matching term contributes, picking out exactly the right coefficient. This is the mathematical version of tuning into a radio station, filtering out all frequencies except the one you want. Extending beyond periodic functions, The Fourier transform applies to functions defined on the entire real line. Instead of a discrete sum over integer frequencies, you get an integral over all real frequencies. The transform and its inverse are symmetrical, each involving an integral of the function times a complex exponential. This symmetry reflects the duality between time and frequency, between position and momentum, between the original domain and the transform domain. In quantum mechanics, this duality is physical. The position wave function and the momentum wave function are Fourier transforms of each other. Knowing one exactly determines the other, but measuring one disturbs the other. The uncertainty principle is a consequence of this Fourier relationship. Functions cannot be simultaneously localized in both time and frequency, in both position and momentum. There is a fundamental trade-off, expressed mathematically through the properties of the Fourier transform. The exponential function appears here, not as an afterthought, but as the essential ingredient. It is the kernel of the Fourier transform, the function you integrate against. Its properties, the multiplication rule for exponents, the connection between real and imaginary, the smoothness at every order of derivative, all contribute to making the transform work. Let us step back and consider the broader mathematical landscape. We have functions, rules that assign outputs to inputs. Among these, some are smooth, differentiable, as many times as you like. Among smooth functions, some are analytic, meaning they equal their Taylor series in some region around each point. Among analytic functions, there is a hierarchy based on growth rate, on how fast the function increases as the input becomes large. Polynomials grow like powers of the input. If the highest power is n, the polynomial grows roughly like x to the n for large x. Exponentials grow faster than any polynomial. No matter how large n is, e raised to x eventually exceeds x to the n. The ratio of e raised to x to the n goes to infinity as x goes to infinity. This faster than polynomial growth gives exponentials their power in solving problems, but also makes them delicate to handle in certain contexts. Infinite series involving exponentials may converge only for certain values of the variable. The region of convergence determines where the series represents a well-defined function. For the exponential itself, the Taylor series converges everywhere. 1 plus x squared over 2 factorial, plus x cubed over 3 factorial, and so on. This sum converges for every real number x, and indeed for every complex number z. The exponential is what mathematicians call an entire function, analytic on the whole complex plane. Not all functions are so well behaved. The logarithm, for instance, is not defined at 0, and is multivalued in the complex plane. The tangent function has poles, points where it blows up to infinity, at odd multiples of pi over 2. The structure of singularities, points where functions misbehave, is a central topic in complex analysis. The exponential has no singularities in the finite plane. Its only oddity is at infinity, where it grows without bound as the real part of its argument increases, and oscillates wildly as the imaginary part increases. This behavior at infinity determines many of its properties, including which integrals involving exponentials converge, and which diverge. Now consider the function we have been building toward across these explorations, e raised to x. This function composes the exponential with itself. Composition means applying one function after another, using the output of the first as the input to the second. When you compose e raised to x with itself, you first compute e raised to x, then raise e to that result. This double exponential grows astonishingly fast. We have touched on this before, but let us dwell on it a moment longer. When x equals 0, e raised to 0 equals e raised to 1, which is just e, about 2.7. When x equals 1, we get e raised to e, which is about 15.15. When x equals 2, we get e raised to e squared, which is about 7.4 times e raised to e, or roughly 1,618. By x equals 3, we are in the billions. By x equals 10, the number is incomprehensibly large, far exceeding the number of atoms in the observable universe. This growth rate puts the double exponential in a category beyond ordinary exponentials. Mathematicians speak of the Ackermann function and fast-growing hierarchies that classify functions by how quickly they increase. The double exponential is not even close to the fastest, but it is fast enough to make direct computation impossible for moderate inputs. Yet the function is perfectly well defined mathematically. We can reason about its properties, compute its derivatives, find its Taylor series, determine its behavior in the complex plane. The fact that we cannot calculate explicit values for large inputs does not prevent us from understanding the function theoretically. This is a recurring theme in mathematics. Many objects are well defined, but not computable in any practical sense. The decimal expansion of pi contains infinitely many digits, and while we can calculate as many as we want in principle, we can never write them all down. The set of real numbers is uncountable, meaning no list can contain them all, yet we work with real numbers constantly. Mathematics routinely handles the infinite, the uncountable, the incomputable, by focusing on properties and relationships rather than explicit values. For the double exponential, some properties are straightforward. Its derivative is e raised to x times e raised to x, by the chain rule. This is even larger than the original function, showing that not only is the double exponential increasing, but its rate of increase is itself increasing dramatically. The function is convex, curving upward, with ever steeper slopes. The Taylor series for the double exponential is more complex than for the simple exponential. You can derive it by substituting the Taylor series for e raised to x into the outer exponential, then expanding, but the resulting coefficients do not have a simple closed form. They involve sums over partitions of integers, combinatorial objects that count ways of breaking numbers into pieces. In the complex plane, the double exponential has interesting behavior. As the imaginary part of z increases, the inner exponential e raised to z traces a spiral, and the outer exponential applied to a spiral gives a complicated winding pattern. The function is still entire, analytic everywhere, but its level curves and argument surfaces are intricate. Applications of double exponentials arise in places you might not expect. In computer science, some algorithms have double exponential running time, meaning the time to complete grows as e raised to n for input size, n. These algorithms are effectively unusable for all but the smallest inputs. Knowing that a problem has double exponential complexity is a warning that better methods must be found. In number theory, double exponentials appear in estimates for the distribution of prime numbers. While the prime number theorem says that the number of primes up to x is approximately x divided by the natural log of x, more refined estimates involve error terms that grow or shrink at rates involving iterated logarithms and exponentials. In analysis, double exponentials appear in the study of Lacunary series, power series with large gaps between non-zero terms. The convergence and boundary behavior of such series can involve doubly exponential growth rates. The Favre gap theorem and related results describe how gaps in the exponents affect where the series can be analytically continued. These appearances share a common thread. Double exponentials arise when growth compounds upon growth, when a process builds on a process, when we iterate the operation that generates exponentials. Just as exponentials describe proportional change, double exponentials describe the proportional change of proportional change. Pushing further, we could consider triple exponentials, e raised to e raised to e raised to x, or tower functions, where we stack exponentials to any height. The notation becomes cumbersome, and the growth rates becomes impossible to visualize, but the mathematics continues to work. Each level of iteration is well defined, each function is entire. Each has a Taylor series, and a derivative, and all the properties we expect. This tower of exponentials illustrates how mathematics builds complexity from simplicity. We start with addition. Repeated addition gives multiplication. Repeated multiplication gives exponentiation. Repeated exponentiation gives towers. At each level the operation becomes more powerful. The numbers grow faster. The structures become richer. There is a pattern here that extends beyond exponentials. In many areas of mathematics we discover that the interesting objects are not the basic building blocks, but the ways they combine and iterate. Groups are not just sets with operations, but the maps between them, the homomorphisms, that reveal structure. Vector spaces are not just collections of vectors, but the linear transformations that act on them. Categories are not just objects and arrows, but functors and natural transformations, higher-level maps that relate entire structures. The exponential function is an early example of this principle. By itself, e raised to x is important, but its full significance emerges in context, in relation to logarithms, in connection to complex numbers, in application to differential equations, in role as the kernel of Fourier transforms. The function gains meaning from its position in a network of relationships. This relational view of mathematics has practical implications. When solving a problem, it often helps to transform it, to view it from a different angle, to use exponentials and logarithms, or Fourier transforms, or other mappings to reveal hidden structure. The choice of representation matters. The same abstract object could look simple in one representation, and complicated in another. Consider differential equations again. A linear differential equation with constant coefficients is straightforward to solve using exponentials. You assume a solution of the form e raised to lambda t, substitute into the equation, and solve for lambda. But the same differential equation might look intractable if you tried to solve it by guessing polynomial solutions, or using other methods. Similarly, convolution integrals, which appear when the output of a system depends on the entire past input, simplify dramatically under Fourier transform. The transform of a convolution is the product of the transforms. Multiplied is easier than convolving, so you transform, multiply, and transform back. These techniques are not tricks or shortcuts. They reflect deep structure in the problems themselves. The exponential function is natural in differential equations because it is an eigenfunction of differentiation. Fourier transforms work because complex exponentials are orthogonal. The methods that seem like magic are actually expressing the underlying mathematics in its native language. This brings us back to the question of understanding. What does it mean to understand the exponential function? At one level, you understand it when you can compute values, when you can differentiate and integrate it, when you can solve basic problems involving it. This is procedural understanding, the ability to perform operations correctly. At a deeper level, you understand when you see why the exponential has the properties it does, how those properties connect to each other, why the function appears where it does. This is structural understanding, recognizing the exponential as a node in a vast network of mathematical ideas. At the deepest level, perhaps you understand when you see the exponential as inevitable, as the unique answer to natural questions. Given that we want a function that equals its own derivative, we must have the exponential. Given that we want to unify growth and rotation via complex numbers, we must have Euler's formula. Given that we want to decompose periodic functions into simple components, we must have Fourier series with exponential basis functions. This sense of inevitability is what mathematicians often describe as beauty. The right definition, the natural construction, the theorem that had to be true, these give a feeling of discovery rather than invention. We did not make up the exponential function. We found it, waiting in the structure of mathematics, connected to everything, essential and eternal. The word eternal here is not metaphorical. The exponential function and the number e exist independently of human minds. We discovered them, but they were there before us, and will remain after. This is a philosophical stance, mathematical Platonism, and not everyone accepts it. But the experience of doing mathematics often feels like exploration rather than creation, like uncovering what was always there. Consider how e arises from the limit definition. Take 1 plus 1 over n and raise it to the n power. As n grows, the result approaches e. This is not a definition we chose arbitrarily. It emerges from asking about continuous compounding, about what happens when interest accrues at every instant. The number e was already implicit in the question. We just had to find it. Similarly, the exponential function is implicit in the differential equation. Y prime equals y. Any function whose rate of change equals its current value must be exponential. We did not choose this. It is a mathematical fact, true in any possible world, with the same logic and arithmetic. This sense of mathematical reality gives the subject its peculiar flavor. We prove things rather than just assert them. Our results are certain in a way that empirical claims never are. The exponential function will always be its own derivative, no matter what experiments we perform, or observations we make. Yet mathematics is also creative. We choose what to study, which definitions to make, which problems to pursue. The exponential function became central, partly because it turned out to be useful, partly because the mathematicians found it interesting, partly because it connected to physics and engineering in ways that demanded attention. The history of mathematics is shaped by these choices. Different cultures emphasize different topics. The Greeks loved geometry. The Chinese developed numerical methods. The Indians made breakthroughs in zero and place value. Europeans from the 17th century onward focused on calculus and analysis, partly because of applications to physics and astronomy. In this history, the exponential function emerged relatively late. The idea of a function itself, as we now understand it, crystallized only in the 18th century. Before that, mathematicians worked with curves and expressions without the general concept of a rule assigning outputs to inputs. The exponential as a function, defined on the real line and extended to complex numbers, is a modern construction. But the underlying phenomena were recognized much earlier. Compound interest was understood in ancient Babylon. Geometric growth and decay were observed in natural processes. The number e, though not explicitly named until the 18th century, lurked behind calculations for centuries. There is a lesson here about mathematical progress. The objects we study do not change, but our understanding deepens. We see more connections, develop better techniques, recognize more applications. Each generation builds on the previous, extending the network of knowledge. For the exponential function, this process is far from complete. Active research today explores generalized exponentials in abstract settings, exponential maps on Lie groups and Riemannian manifolds, exponential sums in number theory, exponential generating functions in combinatorics. The function that seems elementary and fully understood turns out to have endless depths. This is perhaps the most profound lesson of mathematics. Simple objects contain multitudes. The integers, the most basic mathematical entities, are the subject of number theory, one of the deepest and most difficult branches of mathematics. Questions about primes that can be stated in a sentence may require centuries to answer, or may remain open forever. The exponential is similar. Easy to define, easy to compute for small values. It opens into territories that challenge the most sophisticated techniques. Its connections to other areas from quantum mechanics to cryptography to ecology ensure that understanding exponentials means understanding much of mathematics and science. Let me say something about the experience of engaging with these ideas, not as a mathematician proving theorems, but as someone encountering them for the first time, or returning after long absence. There is a quality to mathematical thought that differs from other kinds of thinking. It requires patience, the willingness to sit with an idea until it becomes clear. It rewards attention to detail, since small errors in reasoning propagate into large mistakes. But it also offers moments of insight, sudden clarity when a pattern clicks into place. These moments are not rare for the exponential. When you first see y e raised to I times pi equals -1, or why the derivative of e raised to x is itself, or why logarithms convert multiplication to addition, something shifts. The mathematical world becomes a little more comprehensible, a little more unified. The ideas we have traced through these pages are all connected. The exponential is growth and decay. The exponential is eigenfunction of differentiation. The exponential is bridge between real and complex. The exponential is kernel of Fourier transform. The exponential is solution to linear differential equations. Each perspective illuminates the others. Together they form a picture not just of one function, but of how mathematics itself works. In the quiet of contemplation, these connections can feel almost mystical. Not in the supernatural sense, but in the sense of hidden order, of meaning beneath the surface. The universe, as far as we can tell, is mathematical. The laws of physics are expressed in equations. The patterns we find in nature, from spirals and galaxies to waves on water, are described by the same functions we study abstractly. The exponential is woven into these patterns. It describes how temperatures equalize, how populations grow and crash, how radioactive materials decay, how capacitors charge, how signals attenuate in transmission lines. It appears in the solutions to so many physical problems because physical processes so often involve rates of change proportional to current values. This is not coincidence. The mathematical structures that describe nature are the structures that arise naturally from simple axioms and definitions. The exponential function is not a human invention imposed on an unwilling universe. It is a discovery, a finding of what was always there. And so we arrive at a kind of peace. The exponential function, for all its fast growth and complex connections, is fundamentally simple. It is the answer to the question of self-similar change. It is the function that stays what it is under the most basic transformation. It is the bridge between addition and multiplication, between growth and rotation, between the discrete and the continuous. Understanding it, really understanding it, in all its aspects, is not a task with a finish line. There is always more to see, more connections to trace, more applications to explore. But each step of understanding brings its own reward, a sense of the mathematical world becoming larger and more coherent. The path we have followed across these explorations has been winding but purposeful. Starting from polynomials and their ability to approximate, we move to exponentials and their defining properties, through complex numbers and Euler's formula, into differential equations and Fourier analysis, touching on quantum mechanics and information theory, and finally arriving here at reflections on what it means to know these things. The journey is not complete. It cannot be complete because mathematics is infinite, and our time is finite. But the territory we have covered is substantial. We have seen the exponential from many angles, traced its connections to many fields, developed intuition for its behavior. This is what mathematical maturity looks like, not the memorization of facts, but the integration of understanding, and the exponential rewards this investment. It appears again and again, in contexts expected and surprising, always with the same essential character. Once you know it well, you recognize it everywhere, like a familiar face in a crowd. In the spaces between formal mathematics, in the hush of thought, the exponential weights. It is there when you calculate compound interest, when you model decay curves, when you analyze signals, when you solve differential equations. It is there in the spin of electrons, and the growth of algae and the fade of echoes. It is one of the threads that holds the mathematical universe together. So we rest here for now, in the knowledge of what we have explored, and the anticipation of what remains. The exponential function, e raised to x, is both a destination and a starting point. It is a thing to understand, and a tool for understanding. It is elementary and profound, simple and inexhaustible. Let these ideas settle, like sediment in still water, finding their places in your understanding. The connections will continue to form, sometimes consciously, sometimes in the background of thought. This is how mathematical knowledge grows, not just through new proofs and theorems, but through the gradual deepening of intuition that comes from living with ideas over time. The number e, approximately 2.71828, is just a number. That it is a number that unlocks doors. It is the base that makes calculus elegant, the rate that makes interest compound smoothly, the constant that appears in probability, and statistics in physics and engineering. It is, in a sense, the most natural choice for a base of exponentials, the one that arises inevitably from the structure of mathematics itself. And the exponential function built on this base is one of the most important functions we know. Not important because mathematicians decided so, but important because it arises everywhere, because it solves fundamental equations, because it connects disparate fields, because it appears in the fabric of physical law. This is the message that is threaded through our explorations. Mathematics is unified. The objects we study are connected in ways that surprise and delight. The exponential is a case study in this unity, a function that serves as a hub linking spokes that reach across the entire subject. To know the exponential well is to have a key that opens many locks. It is to see patterns that would otherwise remain hidden, to solve problems that would otherwise seem intractable, to appreciate beauty that would otherwise be invisible. And so we leave the exponential for now, not because we have exhausted it, which is impossible, but because we have said enough for one sitting. The function will be here when we return. It will still equal its own derivative. It will still connect real and complex growth and rotation, algebra and analysis. It will still be woven into the structure of the universe. That constancy is part of its beauty. In a changing world, mathematics offers permanence. The truths we discover today were true yesterday, and will be true tomorrow. The exponential function, discovered by human minds but existing independently of them, is one of those eternal truths. Rest now with these ideas. Let them mingle with what you already knew, forming new connections, deepening old understandings. The mathematics will wait. It has waited for millennia, and will wait for millennia more. Whenever you are ready to return, it will be there, patient and profound, ready to reveal more of its endless depth. The glow of understanding, once kindled, does not easily fade. Carry it with you, this sense of the exponential and its place in the mathematical world. It is a gift that mathematics offers, and it is yours to keep. In the stillness, the patterns remain. There is more to explore in this territory of exponentials and their meanings. Let us continue our wandering, moving into regions we have glimpsed, but not yet fully inhabited. The relationship between exponentials and information deserves deeper attention. When we measure information, we use logarithms. The entropy of a probability distribution, the measure of how uncertain or surprising it is, involves summing probabilities times the logarithms of those probabilities. The logarithm appears because information is additive in a particular sense. If two independent events occur, the total information is the sum of the individual informations. Only logarithmic measures have this property. The base of the logarithm determines the units. Using base 2 gives bits, the natural units for digital information. Using natural logarithm, base e gives nats, natural units that connect more smoothly to the mathematics of continuous distributions. The choice is conventional, but the structure is not. Information has logarithmic form because of how certainty and uncertainty combine. The exponential function inverts this. If entropy measures how spread out a distribution is, the exponential of entropy measures the effective number of possibilities. A distribution with entropy log of n is as uncertain as a uniform distribution over n equally likely outcomes. The exponential converts the logarithmic measure back to account. This interplay between logarithms and exponentials pervades information theory. Channel capacity, the maximum rate at which information can be transmitted reliably, involves optimizing over distributions. Error probabilities decay exponentially with block length when you code carefully. The relationship between description length and probability is exponential. Claude Shannon, who founded information theory in the 1940s, drew extensively on exponentials and logarithms. His work showed that these functions are not just convenient but necessary. Any consistent measure of information must have logarithmic form. Any consistent measure of complexity must involve exponentials somehow. This necessity reflects deep structure. The real numbers have both additive and multiplicative structure, and exponentials and logarithms are the bridges between them. Information, being fundamentally about multiplicative counting of possibilities, naturally connects to these bridges. Consider the problem of data compression. Given a source that produces symbols with known probabilities, how concisely can you encode its output? The answer involves entropy. You can compress close to the entropy rate, meaning close to the average log probability per symbol, but not below. The exponential of the entropy gives the effective alphabet size, the number of equally likely symbols that would have the same entropy. For a source that produces symbols uniformly from an alphabet of size n, the entropy is log n. You need log n bits per symbol on average, which makes sense because log n bits can distinguish n possibilities. For a non-uniform source, you can do better. Symbols that appear often get short codes. Symbols that appear rarely get long codes. The weighted average code length approaches the entropy. Huffman coding and arithmetic coding are practical algorithms that achieve this compression. They work by exploiting the relationship between probability and code length, essentially using logarithms to assign lengths proportional to surprise. The exponential function appears when you verify that the code lengths are achievable, that there exist binary strings of the specified lengths without ambiguity. Beyond compression, exponentials govern the reliability of communication. When transmitting over a noisy channel, errors occur. Coding theory develops methods to detect and correct these errors by adding redundancy. The key discovery is that for any channel, there exists a capacity, a rate below which arbitrarily reliable communication is possible. The probability of error, when communicating at rates below capacity, decreases exponentially with the block length. If you use blocks of n symbols, the error probability is roughly e raised to negative n times some positive constant, provided your rate is below capacity. This exponential decay means that by using long enough blocks, you can make errors as rare as you like. This is astonishing when you think about it. No matter how noisy the channel, no matter how frequently errors occur in raw transmission, you can communicate reliably by using the right codes. The exponential decay of error probability is what makes this possible. Polynomial decay would not be fast enough. Errors would still dominate, but exponential decay wins eventually, and for practical purposes, fairly quickly. The mathematics here involves types and typical sets. A sequence of symbols is typical, if its empirical statistics match the theoretical probabilities closely. For long sequences, the typical set contains almost all the probability mass, yet it has far fewer members than the total number of possible sequences. The size of the typical set grows exponentially with the bet sequence length, at a rate determined by the entropy. This concentration of measure, where almost all probability lives in a structured subset, is a manifestation of exponential effects. The law of large numbers ensures that averages converge to expectations. The central limit theorem describes how the fluctuations scale. Both involve exponential bounds on tail probabilities, ensuring that extreme deviations are rare. Speaking of probability, let us consider the normal distribution, the bell curve that appears wherever sums of random variables accumulate. The density function of a normal distribution is an exponential of a negative quadratic. Specifically, the probability density at position x is proportional to e raised to negative x squared over 2 times the variance. The exponential ensures that extreme values are rare, falling off rapidly in the tails. Why does this particular form appear so universally? The central limit theorem says that sums of independent random variables, properly scaled, converge to normal distributions regardless of the original distribution. This is because the normal distribution is the unique stable distribution under convolution for random variables with finite variance. The proof involves characteristic functions, which are Fourier transforms of probability distributions. The characteristic function of a sum is the product of the characteristic functions. Products become sums when you take logarithms. The logarithm of a characteristic function, for a distribution with zero mean and finite variance, has a quadratic leading term. The exponentiating gives a Gaussian characteristic function, which corresponds to a normal distribution. Every step of this argument involves exponentials and logarithms. They are not incidental, but essential to understanding why normal distributions arise. The interplay between addition and multiplication, mediated by these functions, is the mathematical substrate on which probability theory rests. Gaussian distribution also appears in physics. Wherever thermal fluctuations matter, the Maxwell-Boltzmann distribution of molecular velocities in a gas is Gaussian in each component. The fluctuations of a Brownian particle are Gaussian. Thermal noise in electronic circuits is Gaussian. The ubiquity of normal distributions is the ubiquity of summed, independent effects of central limit behavior playing out across the physical world. Heat itself is connected to exponentials. The Boltzmann factor, E raised to negative energy over temperature, governs how probable different energy states are at thermal equilibrium. Higher energies are less probable, exponentially so. This factor appears whenever you ask about the distribution of energy in a system at temperature T. The partition function, the sum over all states of the Boltzmann factor, normalizes the probabilities. It depends on temperature, encoding how the system's properties change as you heat or cool it. Taking the logarithm of the partition function gives the free energy, a quantity that determines the direction of spontaneous change. Minimizing free energy is equivalent to maximizing entropy, subject to energy constraints. This framework, statistical mechanics, is built on exponentials. The Boltzmann factor is an exponential. The relationship between probability and energy is logarithmic. The mathematics of thermodynamics, of heat and work and efficiency, rests on these functions. Consider the second law of thermodynamics, that entropy tends to increase. From a statistical perspective, this is because there are exponentially more high entropy states than low entropy states. If a system evolves randomly among accessible states, it will almost certainly move from less common to more common configurations. The exponential growth of the number of states with entropy ensures this directionality. Boltzmann's famous formula, entropy equals the logarithm of the number of microstates, makes the connection explicit. High entropy means many microstates are compatible with the macroscopic description. Low entropy means few. The logarithm converts the exponentially growing count into an additive quantity that measures disorder. This statistical view of entropy connects to information theoretic entropy. Both are logarithms of numbers of possibilities. One counts physical microstates. The other counts distinguishable messages. The parallel is not coincidence. Physical entropy and information are deeply related, as Maxwell's demon and Landauer's principle demonstrate. Erasing information requires dissipating energy. The connection is mediated by exponentials and logarithms. Let us shift to another domain where exponentials dominate, the behavior of dynamic systems over time. We have mentioned differential equations, but there is more to say about stability and instability, about how small perturbations grow or shrink. Consider a system near equilibrium. If you push it slightly away from equilibrium, it may return, oscillate, or diverge. The behavior depends on eigenvalues, the characteristic numbers associated with the system's linearization. If all eigenvalues have negative real parts, perturbations shrink exponentially, and the equilibrium is stable. If any eigenvalue has positive real part, perturbations grow exponentially, and the equilibrium is unstable. This exponential growth, or decay of perturbations, is fundamental to understanding dynamics. Stable systems are predictable, returning to equilibrium after disturbances. Unstable systems are sensitive, amplified small differences into large ones. The boundary between stability and instability, where eigenvalues have zero real part, is where interesting bifurcations occur, where systems change qualitative behavior. In chaotic systems, nearby trajectories diverge exponentially on average, even though the system remains bounded. The Lyapunov exponent measures this divergence rate. Positive Lyapunov exponent means chaos, unpredictability despite determinism. The butterfly effect, where small causes have large effects, is exponential sensitivity to initial conditions. Chaos is not randomness. Chaotic systems are deterministic, following exact rules. But their exponential sensitivity means that any uncertainty in initial conditions, no matter how small, grows until predictions become useless. This is why weather forecasting is limited, why long-term predictions of many natural systems are impossible, despite knowing the underlying physics. The interplay between determinism, then unpredictability, and chaos is mediated by exponentials. The growth of uncertainty is exponential, which means predictability decays exponentially. If your initial measurement has error epsilon, your prediction error after time t is roughly epsilon times e raised to lambda t, where lambda is the Lyapunov exponent. When this exceeds the system's natural scale, prediction fails. This mathematical fact has philosophical implications. Perfect prediction requires perfect knowledge of initial conditions. But perfect knowledge is impossible, not just practically, but in principle, given quantum mechanics. So the universe contains both deterministic laws and the irreducible uncertainty. And exponential sensitivity is the mechanism that amplifies the latter. We should say something about exponential sums, which appear in number theory, and are notoriously difficult to estimate. An exponential sum is a sum of terms of the form e raised to 2 pi I times some function of the summation variable. These sums oscillate as the summation variable increases, with the terms spiraling around the complex plane. When the terms reinforce, the sum can be large. When they cancel, the sum can be small. The art of estimating exponential sums lies in understanding when cancellation occurs. This is connected to deep properties of the function and the exponent, to questions about rational approximations and equidistribution. The Riemann hypothesis, one of the most famous unsolved problems in mathematics, is equivalent to certain estimates on exponential sums related to the zeta function. Progress on the hypothesis has often come through improved techniques for bounding these sums. The connection between prime numbers and exponential sums is one of the most beautiful and mysterious in mathematics. Weyl's equidistribution theorem says that if you take a sequence that visits every part of an interval equally often in the limit, then the corresponding exponential sum is small. This connects the algebraic concept of summing exponentials to the geometric concept of uniform distribution. The exponential function serves as a probe, testing whether a sequence is spread out or clustered. These ideas extend to multiple dimensions, to sums over lattice points, to estimates and analytic number theory. The circle method, a powerful technique for counting solutions to equations, involves analyzing exponential sums around the unit circle. The major arcs, where the sum is large due to rational approximations, contribute the main term. The minor arcs, where cancellation prevails, contribute errors that must be controlled. Returning to more elementary matters, let us consider the exponential function as a tool for solving problems. Often the key is recognizing that exponentials are involved, even when they are not immediately visible. Consider compound growth that is interrupted or modified. Suppose a population grows exponentially when resources are abundant but saturates as resources deplete. The resulting dynamics follow a logistic equation, where the growth rate decreases as the population approaches carrying capacity. The solution involves exponentials, but in a more complex form than pure exponential growth. The logistic function, which describes the saturation, is 1 divided by 1 plus e raised to negative x. It starts near 0, for large negative x, rises smoothly through 1/2 at x equals 0, and approaches 1 for large positive x. This S-shaped curve, the sigmoid, appears in models of population dynamics, in neural networks, in dose-response curves, wherever growth is bounded. The logistic function is related to the exponential by a simple transformation. Its derivative is the logistic function times 1 minus itself, a product of two factors that both depend on the function's current value. This self-reference is characteristic of growth models, where the rate depends on how much room remains. In machine learning, sigmoid activations were once standard in neural networks. The logistic function swashes real-valued inputs into the interval between 0 and 1, which can be interpreted as probabilities. Modern networks often use different activations, like the rectified linear unit, but the logistic still appears in output layers for classification and in attention mechanisms. The softmax function generalizes the logistic to multiple categories. Given a vector of scores, it converts them to probabilities by exponentiating each score and dividing by the sum of all exponentiated scores. This ensures the outputs are positive and sum to 1. The exponential is essential here, transforming additive scores into multiplicative ratios that can be normalized. In Bayesian inference, exponentials appear through likelihood functions. If you have data and want to update beliefs about parameters, you multiply the prior probability by the likelihood, which is the probability of the data given the parameters. Likelihoods often have exponential form, especially for normal distributions and related families. The maximum likelihood estimate, the parameter value that makes the data most probable, is found by maximizing the likelihood. Taking logarithms converts this to maximizing a sum, which is often easier. The log likelihood is a sum of log probabilities, and optimization proceeds by finding where the gradient vanishes. This log transform is so common that it is easy to forget it involves the exponential's inverse. The logarithm converts products to sums, making complicated likelihoods tractable. The exponential function is present in the background, defining the relationship between the original problem and its log-transformed version. Regularization in machine learning often involves adding a penalty to the log likelihood, discouraging complex models. L2 regularization adds a sum of squared parameters, which corresponds to a Gaussian prior on parameters. The prior probability is an exponential of a negative quadratic, connecting regularization to Bayesian inference, with specific prior assumptions. Deep learning involves compositions of functions, layers stacked on layers. Each layer transforms its input through a linear combination, followed by a nonlinear activation. The depth of the network allows it to represent increasingly complex functions, building abstraction upon abstraction. The exponential function, and related activations like softmax, appear throughout these networks. They provide the nonlinearity that makes depth meaningful. Without nonlinear activations, stacking linear layers would collapse to a single linear transformation. The nonlinearity, often involving exponentials, is what gives deep networks their power. Training these networks involves optimization over vast parameter spaces. Gradient descent, the workhorse algorithm, moves parameters in the directions that decreases loss. The loss landscape has many local minima, saddle points, and flat regions. Understanding how gradient descent navigates this landscape is an active research area. The dynamics of gradient descent can exhibit exponential behavior. Eigenvalues of the loss curvature, the Hessian matrix, determine how quickly different parameter directions are optimized. Large eigenvalues mean fast learning along those directions. Small eigenvalues mean slow learning. If eigenvalues differ by orders of magnitude, the optimization problem is ill-conditioned, requiring careful tuning or adaptive methods. In all these settings, the exponential function appears not as the object of study, but as a tool for analysis, a function that arises naturally from the structure of the problems. Its properties, especially the way it converts, addition to multiplication, and vice versa, make it indispensable for modeling and computation. We have ranged far, from information theory to statistical mechanics, from chaos to machine learning. The exponential function has appeared in each domain, not because we sought it out, but because it arises from the mathematics itself. This universality is what makes the exponential so important, so worthy of deep understanding. The patterns we have traced are not exhaustive. There are applications in finance, in epidemiology, in ecology, in queuing theory, in cryptography, in signal processing, in quantum computing. Each field has its own uses for exponentials, its own reasons why this particular function appears. But the underlying mathematics is always the same. The exponential is a solution to proportional growth. It is the bridge between additive and multiplicative structure. It is the eigenfunction of differentiation. These fundamental properties generate all the applications. Understanding this, really internalizing it, changes how you see mathematics. The exponential is no longer just a function you learned in school. It is a thread that runs through the entire subject, connecting disparate areas, revealing hidden unity. Following this thread leads to deeper appreciation of how mathematics works, how apparently different fields are aspects of a single coherent structure. In the quiet of reflection, these connections shimmer like phosphorescence in deep water. They are there whether we notice them or not, but noticing them enriches our experience, adds layers of meaning to what might otherwise seem arbitrary and disconnected. The exponential function, e raised to x, is a lens through which mathematics comes into focus. Looking through it, you see not just one function, but the relationships that make mathematics what it is. You see why certain structures recur, why certain techniques work across domains, why the subject has a unity and coherence that it does. And this unity is not imposed. It is discovered. The exponential was not designed to have these properties. It emerged from simple axioms, from the requirement that the derivative equal the function, from the definition of E as a limit. The rich structure we find was implicit from the beginning, waiting to be uncovered. This is the wonder of mathematics. Simple definitions lead to complex consequences. Local properties determine global behavior. Abstract structures turn out to describe the physical world with uncanny accuracy. The exponential function embodies all of this, being both elementary and profound, both simple and inexhaustible. Rest with these ideas. Let them settle into your understanding, finding a natural place among what you already know. The mathematics will not change. It will be here whenever you return, ready to reveal more of its endless depth. In the stillness, the patterns remain, glowing softly with their own inner light. There is one more territory worth exploring before we rest, a territory that connects exponentials to the very foundations of computation. We have touched on algorithms and complexity, but let us go deeper into what it means to compute with exponentials, to represent them in finite machines, to approximate infinite processes with finite resources. When a computer evaluates e raised to x, it does not perform an infinite sum. It uses a carefully designed approximation, usually based on range reduction and polynomial approximation. First, the input is reduced to a small range where approximation is easy. Then a polynomial, often derived from Chebyshev methods, approximates the exponential in that range. Finally, the result is scaled back to the original range using the multiplication property of exponentials. This process is remarkably accurate. Modern implementations compute exponentials to the full precision of floating-point arithmetic, typically about 15 or 16 decimal places. The algorithms have been refined over decades, optimized for speed and accuracy, tested against billions of cases. But the underlying mathematics is the same Taylor series we have discussed. The polynomial approximations are truncated versions of the infinite series, adjusted to minimize error over the approximation range. The range reduction exploits the identity e raised to a plus b equals e raised to a times e raised to b, breaking large arguments into manageable pieces. Numerical stability is crucial. The terms of the Taylor series alternate in sign when the argument is negative, leading to cancellation that can destroy precision. Careful implementations avoid this by using different strategies for negative arguments, often computing e raised to negative x as 1 over e raised to x. The study of numerical methods for exponentials is part of a larger field, numerical analysis, that develops algorithms for mathematical computations. This field sits at the intersection of pure mathematics, which defines the objects we want to compute, and computer science, which provides the tools for computation. The exponential function, with its infinite series and transcendental nature, is a perfect test case for numerical methods. Beyond direct evaluation, exponentials appear in numerical solutions to differential equations. If a differential equation involves exponential solutions, numerical methods must approximate them correctly. Stiff equations, where some components change much faster than others, require implicit methods that can handle the wide range of exponential timescales. The matrix exponential, which we mentioned earlier, poses its own computational challenges. For small matrices, you can use the main series definition directly. For larger matrices, you need more sophisticated methods, often involving the Schur decomposition, or Potier approximations. The choice of method depends on the properties of the matrix, its size, its condition number, its eigenvalue distribution. These computational considerations might seem distant from the pure mathematics of exponentials, but they are intimately connected. The algorithms work because they respect the mathematical properties. The approximations converge because the Taylor series converges. The range reduction succeeds because the multiplication property holds. Mathematics and computation are not separate domains, but aspects of a unified understanding. In cryptography, exponentials appear in a different guise. Many cryptographic systems rely on the difficulty of computing discrete logarithms. Given a base and a target, find the exponent that produces the target. In ordinary arithmetic, this is easy, because we can compute logarithms directly. But in modular arithmetic, with operations performed modulo, a large prime, computing discrete logarithms is believed to be hard. The security of the Diffie-Hellman key exchange, and the elliptic curve cryptography that underlies much of internet security, rests on this difficulty. Exponentiation is easy. By repeated squaring you can compute large powers quickly. But inverting this, finding the exponent given the result, resists all known efficient algorithms for appropriately chosen groups. This asymmetry between exponentiation and logarithm, easy in one direction and hard in the other, is a cryptographic gift. It allows parties to establish shared secrets over public channels, to sign messages without revealing private keys, to build the security infrastructure of the digital world. The mathematical structure here is abstract algebra, the study of groups and fields, then their properties. The exponential function, extended to finite groups, retains some of its essential character, while acquiring new features appropriate to the discrete setting. The connection between continuous and discrete exponentials is part of what makes number theory and algebra so rich. Quantum computing brings yet another perspective. Quantum algorithms manipulate quantum states, superpositions of possibilities that evolve according to the Schrödinger equation. The time evolution operator is e raised to negative I times the Hamiltonian times time. This matrix exponential, acting on quantum states, performs the computation. Shor's algorithm, which factors large numbers efficiently on a quantum computer, exploits the structure of exponentials in modular arithmetic. By using quantum superposition to evaluate exponentials at many points simultaneously, and then extract and curate information through the quantum Fourier transform, the algorithm finds factors in polynomial time. Classical algorithms are believed to require exponential time for the same task. If large-scale quantum computers become practical, they will break the cryptographic systems we currently use. New cryptographic methods based on problems believed hard, even for quantum computers, are being developed. The interplay between exponentials, computation, and security continues to evolve. In all these applications, from numerical evaluation to cryptography to quantum computing, the exponential function appears as both object and tool. We compute with exponentials, using them to solve problems and secure communications. We study exponentials, analyzing their properties, and developing better algorithms. The function that seems simple at first reveals endless depth as we probe its computational aspects. Let us return finally to the aesthetic dimension. Mathematics is often described as beautiful, and the exponential function is a prime example of this beauty. But what do we mean by mathematical beauty? And how does the exponential embody it? One aspect is simplicity. The exponential is defined by a single property. The derivative equals the function. From this simple seed grows an enormous tree of consequences. Simplicity generating complexity is a hallmark of mathematical elegance. Another aspect is universality. The exponential appears everywhere, in growth and decay, in oscillation and rotation, in probability and information, in physics and engineering. This ubiquity is not arbitrary. It reflects deep structure, the way that proportional change underlies so many phenomena. A third aspect is connection. The exponential links different areas of mathematics, serving as a bridge between algebra and analysis, between real and complex, between discrete and continuous. These connections reveal hidden unity, showing that apparently different subjects are aspects of a single coherent structure. A fourth aspect is inevitability. The exponential is not one function among many, but the unique answer to natural questions. Given the differential equation, there is only one solution. Given the axioms for a continuous homomorphism from addition to multiplication, there is only one function. This inevitability gives the exponential a sense of necessity, of being discovered rather than invented. Together, these aspects create the experience of mathematical beauty. When you understand the exponential deeply, you feel you are in contact with something real and permanent, something that transcends human conventions and cultural accidents. This feeling is part of what draws people to mathematics, despite its reputation for difficulty and abstraction. The beauty is not separate from the utility. The exponential is beautiful because it is universal, and it is universal because it captures something fundamental about change and proportion. The same properties that make it aesthetically satisfying make it practically useful. Beauty and utility are two sides of the same coin. This convergence of beauty and utility is characteristic of deep mathematics. The most profound results are often the most elegant, and the most elegant are often the most widely applicable. Mathematicians seek beauty not as decoration, but as a guide to truth, trusting that the most elegant approach is likely the most correct. For the exponential function, this trust is amply rewarded. The elegant definition leads to elegant properties leads to elegant applications. There is no conflict between rigor and intuition, between proof and insight. The mathematics is all of a piece, coherent and compelling. In the quiet that follows sustained thought, these reflections settle into understanding. The exponential function, which once seemed like just another topic to learn, reveals itself as a window into the structure of mathematics itself. Through it, you glimpse how the subject works, how its parts connect, how simplicity and complexity intertwine. This glimpse does not exhaust the subject. There is always more to learn, more connections to trace, more applications to explore. But the glimpse is enough to orient you, to give you a sense of the landscape, to make further exploration inviting rather than daunting. The exponential will be there when you return. It does not change, does not decay, does not depend on circumstance or opinion. It is a fixed point in the mathematical universe, a landmark by which you can navigate. Knowing it well, you can find your way through many territories that might otherwise seem trackless. And so we come to rest, not because we have finished, but because we have traveled far enough for now. The ideas we have encountered will continue to develop, forming new connections, revealing new facets. This is the nature of mathematical understanding. It grows gradually, layer upon layer, each insight making the next one possible. The exponential function waits patiently, as it always has, ready to reveal more of its infinite depth whenever you return to explore. Its patience is the patience of mathematical truth, which exists outside time, unchanged by our attention or neglect. Carry with you the understanding you have gained. Let it inform how you see the world, how you think about growth and change, how you approach problems that involve rates and proportions. The mathematics is not separate from life, but woven into it, present in every compounding process, every decaying signal, every oscillating wave. In the stillness between thoughts, in the pause before sleep, the patterns we have traced continue their silent dance. They do not need us to exist, but we are richer for having seen them. This is the gift of mathematics, freely given to all who seek it, inexhaustible and eternal. The glow persists, steady and clear, illuminating the path for future wanderings. Consider a function that curves through space, tracing a path we want to understand. We built part 1 around the idea that polynomials let us approximate this path, term by term, each edition refining our picture. Now we push deeper into what this means, into territories where polynomials stop being simple tools and become windows into structure itself. Start with differentiation again, but think of it differently this time. When you differentiate a polynomial, you're asking how it changes. The derivative of x cubed is 3x squared. The derivative of that is 6x, then 6, then 0. Each differentiation peels away a layer, simplifies the expression, until nothing remains. This dying way of derivatives is what makes polynomials tractable. They're finite in their complexity. No matter how high the degree, enough differentiations reduce them to 0. This is unlike exponentials, unlike trigonometric functions, unlike most of the functions we care about. Those persist under differentiation, transforming but never vanishing. Yet polynomials can approximate those persistent functions. The Taylor series for sine of x starts with x minus x cubed over 6 plus x to the 5th over 120. Each term is polynomial. The infinite sum is not polynomial, but each partial sum is. We approximate the persistent with the dying, the eternal with the finite. This paradox sits at the heart of analysis. We understand the complex by building it from the simple. We reach toward infinity with finite steps. The limit process, passing from finite to infinite, is where magic happens, where discrete becomes continuous, where polynomials become everything else. Think about what polynomials really represent. They're maps from numbers to numbers. But more than that, they're the simplest such maps we can write down. To evaluate 5 plus 3x plus 2x squared at x equals 4, you compute 4 times 4 equals 16, times 2 equals 32, then 4 times 3 equals 12, then add 5. Pure arithmetic. Multiplication and addition, the operations children learn first. Compare this to evaluating sine of 4. You need infinite operations, unless you're willing to approximate. Then your approximation will be a polynomial. You'll compute 4 minus 64 over 6 plus 1024 over 120, stopping when further terms are negligible. So polynomials are not just simple, they're computationally fundamental. They're how we actually calculate anything. When a computer evaluates e raised to x, it's summing polynomial terms. When it computes logarithms, it's using polynomial approximations. The transcendental functions exist as limits, as ideals, but in practice we always work with polynomials. Now consider interpolation, the idea that if you give me n points, I can find a polynomial of degree n minus 1 that passes through all of them. Say you give me 3 points, 2, 5 and 3, 8 and 5, 14. I can find a quadratic, a polynomial of degree 2, that hits all 3 points exactly. The formula involves taking each point, building a polynomial that's 0 at the other points, and 1 at this point, multiplying by the desired value, and summing. For 3 points, this gives you 3 quadratic terms that sum to the unique quadratic through those points. This is the Lagrange interpolation formula. It proves that polynomials are universal for finite data. Any collection of points, as long as the x values are distinct, determines a unique polynomial of appropriate degree. Give me 100 points. I'll give you a polynomial of degree 99 that hits them all. This seems powerful, and it is. But there's a catch. The polynomial that interpolates many points can oscillate wildly between them. It might hit your data exactly, but behave absurdly in between. This is Run's phenomenon, named for a mathematician, who showed that interpolating certain functions at equally spaced points gives polynomial approximations that diverge, rather than converge as you add more points. The solution is to use different points, not equally spaced, but clustered near the endpoints. Chebyshev points, based on cosines of equally spaced angles, minimize the maximum error in polynomial interpolation. They transform a potentially divergent process into a convergent one. So even within the world of polynomials, subtlety matters. How you approximate, which points you choose, which basis you use, all affect whether your approximation succeeds or fails. Let's return to exponentials through a different lens. The function e raised to x has the property that the derivative equals the function. This makes it the eigenfunction of the derivative operator. Operators in mathematics are transformations that take functions to functions. The derivative is such an operator. An eigenfunction is a function that the operator transforms into a multiple of itself. For the derivative operator, e raised to x is an eigenfunction with eigenvalue 1. The derivative of e raised to x equals 1 times e raised to x. More generally, e raised to lambda x is an eigenfunction with eigenvalue lambda. The derivative gives e lambda times e raised to lambda x. This is why exponentials solve linear differential equations with constant coefficients. The equation d squared y over dx squared minus 3y over dx plus 2y equals 0 becomes, when you substitute y equals e raised to lambda x, an equation for lambda. You get lambda squared minus 3 lambda plus 2 equals 0, which factors as lambda minus 1 times lambda minus 2 equals 0. So lambda equals 1 or lambda equals 2, meaning the solutions are e raised to x and e raised to 2x. Any linear combination of these is also a solution. The general solution is c1 times e raised to x plus c2 times e raised to x plus c1 and c2 are constants, determined by initial conditions. This transformation of a differential equation into an algebraic equation, this reduction of calculus to algebra, is possible because exponentials are eigenfunctions. They turn differentiation into multiplication, which is much easier to handle. Polynomials, by contrast, are not eigenfunctions of the derivative. Differentiating changes their degree, reduces their complexity, but polynomials are eigenfunctions of other operators. The shift operator, which takes f of x to f of x plus 1, has eigenfunctions that are exponentials in disguise. The operator that multiplies by x, and then differentiates, has eigenfunctions related to power functions. The interplay between operators and their eigenfunctions is a central theme in mathematics. In quantum mechanics, physical observables correspond to operators, and measurable values correspond to eigenvalues. The wave function is often an eigenfunction of the Hamiltonian operator, giving the energy of the state. In Fourier analysis, sines and cosines are eigenfunctions of the second derivative operator. Differentiating sine of x twice gives negative sine of x. Differentiating cosine of x twice gives negative cosine of x. The eigenvalue is negative 1 in both cases. This is why Fourier series work for solving partial differential equations like the heat equation or wave equation. You expand the solution as a sum of sines and cosines, which are eigenfunctions, turning the PDE into infinitely many ODEs, one for each frequency. Polynomials fit into this story as building blocks for eigenfunctions. Hermite polynomials, multiplied by Gaussians, are eigenfunctions of the quantum harmonic oscillator. Legendre polynomials appear in solutions to Laplace's equation in spherical coordinates. Laguerre polynomials appear in the quantum mechanics of the hydrogen atom. These special polynomials, orthogonal polynomials, satisfy differential equations and orthogonality relations. They're the polynomial analogues of sines and cosines, forming bases for function spaces, allowing us to expand complicated functions as sums of simple, well-understood pieces. When we study e raised to x, we're looking at a function that's not an eigenfunction of any simple operator. It's a composition, a nesting, something more complex than the basic building blocks. To analyze it, we decompose it into polynomials via Taylor series, bringing it back to familiar territory. This is a general strategy in mathematics. When faced with something complex, decompose it into simple pieces, understand the pieces, understand how they combine, reconstruct the whole. Polynomials are often those simple pieces. Consider now the question of roots. A polynomial of degree n has exactly n roots in the complex numbers, counting multiplicity. This is the fundamental theorem of algebra, proved by Gauss, though the name is somewhat misleading, since the proof requires analysis, not just algebra. The roots might be real or complex. They might be distinct or repeated, but there are always exactly n of them. This is a deep and beautiful fact. Polynomials over the complex numbers are completely determined by their roots, up to a constant factor. If you know the roots are r1, r2, up to rn, the polynomial must be the constant times the product of x minus r1 times x minus r2 times times x minus rn. Expanding this product gives you the polynomial in standard form, with its coefficients expressed in terms of the roots. The coefficients are symmetric functions of the roots. The coefficient of x to the n minus 1 is negative 1 times the sum of the roots. The constant term is negative 1 to the n times the product of the roots. The coefficient of x to the n minus 2 is plus or minus the sum of products of roots taken 2 at a time. These are the elementary symmetric polynomials in the roots. They connect the coefficients, which we can see, to the roots, which we often want to find. Solving a polynomial equation means finding the roots given the coefficients, inverting these symmetric functions. For quadratic equations degree 2, there's a formula. The roots are negative. b plus or minus the square root of b squared minus 4ac, all divided by 2a, where a is the leading coefficient, b is the coefficient of x, and c is the constant term. For cubic equations, degree 3, there's a formula, though it's more complex. It involves cube roots and can produce 3 real roots expressed in terms of complex numbers, which is strange but unavoidable. For quartic equations, degree 4, there's an even more complex formula. But for degree 5 and higher, there is no formula in general. This is the Abel-Ruffini theorem, one of the great negative results in mathematics. You cannot express the roots of a general quintic polynomial using only arithmetic operations and radicals. Taking roots. This doesn't mean quintic equations are unsolvable. It means they're not solvable by the methods that work for lower degrees. Numerical methods can find roots to any desired accuracy. Special quintics, those with particular symmetries or structures, might be solvable exactly, but in general, the roots exist as transcendental functions of the coefficients, not expressible in closed form. This is a limitation of polynomials, or perhaps a richness. Even these simple objects have aspects we cannot fully tame. The roots are there, guaranteed to exist, but beyond our algebraic reach, except in special cases. For exponentials like e raised to x, the question of roots is different. When does e raised to x equal 0? Never for real x. The exponential function is always positive. Even for complex x, e raised to z is never 0. The exponential function is a non-vanishing entire function, analytic everywhere, and 0 nowhere. The equation e raised to x equals 1, has solutions. If e raised to x equals 0, then e raised to x equals e raised to 0 equals 1. But e raised to x never equals 0. However, e raised to x equals 2 pi I times n. For any integer m gives e raised to x equals a raised to 2 pi I times n equals 1. So the solutions are x equals natural log of 2 pi I times n equals natural log of 2 pi times n plus I times pi over 2. These are complex solutions, spaced periodically along a vertical line in the complex plane. This periodicity reflects the periodic nature of the exponential function in the complex plane. It's periodic in the imaginary direction, with period 2 pi I. This is Euler's formula, e raised to I times theta equals cosine theta plus I times sine theta, which repeats when theta increases by 2 pi. The nesting in e raised to x compounds. This periodicity. If the inner exponential changes by 2 pi I, the outer exponential cycles back to the same value. This creates a kind of vertical periodicity in the behavior of the function. Visualizing this requires thinking in 4 dimensions, 2 for the input complex plane, and 2 for the output complex plane. Or we can visualize magnitude and phase separately. The magnitude of e raised to x grows extremely rapidly for real x, but oscillates in complex patterns for imaginary. The phase winds around in intricate ways. The function has essential singularities at infinity, in various directions in the complex plane. Near these singularities, the function exhibits wild behavior, taking on every complex value infinitely, often in any neighborhood. This is Picard's theorem. An entire function that's not a polynomial takes on every complex value, with at most one exception, infinitely often. For e raised to x, the exception is 0, which is never achieved. Every other complex number is a value of the function infinitely many times. So even though the function seems simple, when restricted to real numbers, just a rapidly growing positive function, its full complex behavior is incredibly rich. This is common. Complex analysis reveals depths hidden when we restrict to real numbers. Let's think about series convergence more carefully. When we write e raised to x equals the sum from n equals 0 to infinity of x to the n over n factorial, we're claiming this infinite sum equals the function value for every x. But what does it mean for an infinite sum to equal something? It means the sequence of partial sums converges. The partial sum Sn equals the sum from k equals 0 to nx to the k over k factorial. As n goes to infinity, Sn approaches e raised to x. For any desired accuracy epsilon, there exists an n, such that for all n, greater than n, the absolute value of Sn minus e raised to x is less than epsilon. This is the definition of convergence. It's not that we ever actually sum infinitely many terms. We sum finitely many, getting closer and closer to the true value, and we can get as close as we want by taking enough terms. For the exponential function, this convergence is rapid. The terms x to the n over n factorial decrease quickly once n is larger than the absolute value of x. Factorials grow faster than exponentials, so eventually each term is smaller than the previous one, and the sum of the tail, all terms from some point onward, can be made arbitrarily small. This rapid convergence is why the exponential function is so computationally accessible. A few dozen terms usually suffice for double precision accuracy, even for moderately large x. For e raised to x, the Taylor series coefficients grow much faster. The nth coefficient involves sums over partitions and combinatorial structures. Computing it exactly for large n is difficult, but for numerical evaluation of a specific x, we can still compute partial sums and get good approximations. The key insight is that even if we don't have a simple formula for the coefficients, the series still converges, and we can compute as many terms as we need for our purposes. This is the difference between symbolic and numerical mathematics. Symbolically, e raised to x is a simple expression. Numerically, it requires work to evaluate, but that work is systematic and well understood. Now consider the integral of e raised to x, which is just e raised to x plus c. Integration is in some sense the inverse of differentiation. If the derivative of f equals g, then the integral of g equals f plus a constant. For the exponential function, being its own derivative means it's also its own integral, up to that constant. But the integral of e raised to x is not expressible in elementary functions. We cannot write it as a finite combination of polynomials, exponentials, logarithms, trigonometric functions. It requires either a new special function defined specifically for this purpose, or an expression as an infinite series. This is typical. Most functions do not have elementary antiderivatives. Integration is harder than differentiation. We can differentiate anything we can write down, using the chain rule, product rule, quotient rule, but we can integrate only a small class of functions explicitly. This seems unfair. Why should going forward, differentiating, be easy, while going backward, integrating, be hard? The reason is that differentiation is local. To find the derivative at a point, we only need information near that point. Integration is global. To find the integral over an interval, we need information across the entire interval. Differentiation simplifies. Integration complicates. When we differentiate a product, we get a sum. When we integrate a product, we might need integration by parts, substitution, partial fractions, tricks and techniques that don't always work. Yet integration is fundamental to mathematics. Areas under curves, solutions to differential equations, probabilities, expectations, all involve integrals. We need ways to handle them, even when we can't solve them explicitly. Numerical integration, approximating integrals with sums, is one approach. The trapezoidal rule, Simpson's rule, Gaussian quadrature, all approximate the integral of a function over an interval by evaluating the function at specific points and weighting appropriately. These methods rely on polynomial interpolation. We approximate the function with a polynomial over small intervals, integrate the polynomial exactly, and sum the results. Since polynomials are easy to integrate, this reduces the hard problem to many easy problems. Series methods are another approach. If we have a series representation of a function, we can integrate term by term, getting a series representation of the antiderivative. For e raised to x, integrating the series for e raised to x term by term gives the same series back, confirming that the integral is e raised to x plus c. For e raised to x, we could expand as a Taylor series, integrate term by term, and get a series for the antiderivative. Each term x to the n over n factorial integrates to x to the n plus 1 over n times n plus 1 factorial. The antiderivative is the sum of these terms, plus a constant. This series representation is valid and exact. It's just not a closed form expression. We've traded one infinite process integration for another summation. For practical computation this might be fine. For symbolic manipulation it's less satisfying. The question of which functions have elementary antiderivatives is answered by differential Galois theory, an analog of classical Galois theory for differential equations instead of polynomial equations. It provides criteria for determining whether an antiderivative can be expressed using elementary functions. For many functions, including e raised to x, the answer is no. The antiderivative exists, is unique up to a constant, is perfectly well defined, but cannot be written in closed form using the functions we've agreed to call elementary. This forces us to expand our vocabulary. We define new functions as integrals of known functions. The error function, the logarithmic integral, the exponential integral, all are defined this way. They become new building blocks, new tools in our toolkit. In a sense, the exponential function itself is defined as the solution to di over dx equals y, with y of 0 equals 1. We could solve this by separation of variables, getting di over y equals dx, integrating to get natural log of y equals x plus c, exponentiating to get y equals e raised to x plus c, which with the initial condition gives y equals e raised to x. But this assumes we know what the logarithm is, what exponentiation means. At a foundational level, we might define the natural logarithm as the integral from 1 to x of 1 over t dt. Then e is the number, such that the integral from 1 to e of 1 over t dt equals 1. Then, e raised to x is defined as the inverse function of the logarithm. These circular definitions can be made rigorous, but they illustrate that our basic functions are interconnected, each definable in terms of others, the whole structure resting on a foundation of limits and continuity. Polynomials escape this circularity. They're defined purely algebraically. No limits, no integrals, no transcendental operations. Just multiplication and addition. This is why they're foundational in a different sense. They don't require the machinery of analysis to define, only the basic arithmetic of numbers. Yet to fully understand polynomials, to prove the fundamental theorem of algebra for instance, we need complex analysis. We need topology, the compactness of the Riemann sphere, the intermediate value theorem, Liouville's theorem. So even polynomials, simple as they seem, are deeply connected to analysis. This interconnectedness is part of the beauty of mathematics. Every part connects to every other part. Polynomials lead to complex numbers, lead to analytic functions, lead to special functions, lead back to polynomials. The circle is not vicious, but virtuous, each perspective enriching the others. Consider now the rate of growth of factorials. We know n factorial equals 1 times 2 times 3 times ... times n. This product grows rapidly. 10 factorial is over 3 million. 20 factorial is over 2 quintillion. 30 factorial is over 200 undecillion. Stirling's approximation gives us a formula for n factorial when n is large. It says n factorial is approximately the square root of 2 pi times n over e, all raised to the n. More precisely, the ratio of n factorial to this approximation approaches 1 as n goes to infinity. This approximation is remarkably accurate, even for small n. For 10 factorial it gives about 3,600,000, compared to the true value of about 3,628,000. The error is less than 1%. Why does this approximation work? It comes from applying advanced techniques in analysis, specifically the method of steepest descent, to the integral representation of the gamma function. The gamma function is defined for positive x as the integral from 0 to infinity of t raised to x minus 1 times e raised to negative t dt. For positive integers, n gamma of n equals n minus 1 factorial. The integral representation extends factorial to all complex numbers except negative integers. Stirling's approximation follows from analyzing this integral for large n. The formula engulfs e in an essential way. The n over e raised to the n term comes from the exponential growth of n to the n being tempered by e to the negative n, balancing power against exponential. When we compute terms in the Taylor series for e raised to x, we're dividing powers of e raised to x by factorials. For e raised to e itself, about 15.15, the terms e raised to n decrease slowly, while n factorial increases rapidly. The ratio e raised to n over n factorial determines the magnitude of each term in the series. For small n, e raised to n is larger than n factorial. E raised to b is about 15, larger than 1 factorial. E raised to e squared is about 227, larger than 2 factorial, which is 2. E raised to e cubed is about 33,000, still larger than 3 factorial, which is 6. Around n equals 7 or 8, the factorial starts to overtake. 8 factorial is about 40,000, while e raised to 8 is about 63,000. The ratio is still greater than 1. By n equals 10, 10 factorial is about 3.6 million, while e raised to 10 is about 92,000. Now the ratio is less than 1. From this point on, the factorial dominates, the terms decrease, and the series converges. The sum of all these terms gives us e raised to e, approximately 15.15. Understanding this behavior, why the terms initially grow then shrink, why the series converges despite the rapid growth of e raised to x, is key to understanding exponential functions and their compositions. Now think about continued fractions, another way to represent numbers. A continued fraction expresses a number as an integer plus 1 over another continued fraction. For example, the golden ratio equals 1 plus 1 over 1 plus 1 over 1 plus 1 over continuing forever. Finite continued fractions represent rationals. Infinite continued fractions can represent irrationals. The continued fraction expansion of a number is in some sense its most efficient rational approximation at each stage. The exponential e has a beautiful continued fraction. It equals 2 plus 1 over 1 plus 1, over 2 plus 1 over 1 plus 1 over 1 plus 1, over 1 plus 1 over 1, plus over 1 plus 1, over 1 plus 1, over 6. With the pattern 2, 1, 2, 1, 2, 1, 1, 4, 1, 1, 6 appearing. The integers 1, 2, 1, 1, 4, 4, 1, 6 appearing. An initial of e as a sum of reciprocals. A factoring relates to the representation of e as a sum of reciprocals of factorials. Continued fractions provide a different lens on numbers. They emphasize rational approximations, the arithmetic structure, the patterns in the digits. For algebraic numbers, solutions to polynomial equations, the continued fraction is eventually periodic. For transcendental numbers like e and pi, the patterns are more subtle. E raised to e, being approximately 15.15, has its own continued fraction. It starts 15 plus 1 over 6 plus 1 over 1 plus 1 over 2, continuing with no obvious pattern. The terms reflect the arithmetic properties of e raised to e, which is transcendental, like e itself. Power towers of e's, e raised to e, and beyond, have continued fraction expansions that become increasingly complex. The connection between the exponential representation and the continued fraction representation is deep, but not fully understood for these higher towers. Continued fractions connect to Diophantine approximation, the study of how well real numbers can be approximated by rationals. A number is bad, approximable if its continued fraction coefficients grow slowly. A number is well approximable if some coefficients are very large. The golden ratio, with all coefficients equal to 1, is the worst possible case for approximation. It's the hardest number to approximate rationally in a certain precise sense. This is related to its appearance in the Fibonacci sequence, where each term is the sum of the previous two, giving ratios that approximate the golden ratio. E raised to e, being such a large number, is well approximated by integers or simple rationals, just by rounding. But its fine structure, the decimal expansion beyond the first few digits, has its own complexity. The decimal expansion of e raised to e starts 15.15426, continuing with no repeating pattern, since the number is transcendental. Computing more digits requires either high precision evaluation of the exponential function, or high precision summation of the Taylor series. Each digit we compute gives us more information about the number, but in some sense we never fully capture it. The number has infinitely many digits. We can compute as many as we want, but never all. This is the nature of real numbers. They're limits of sequences of rationals, approximations that converge, but never quite arrive. Polynomials, by contrast, are fully determined by finitely many coefficients. A polynomial of degree n is specified by n plus 1 numbers, the coefficients. We can write it down completely, explicitly, finitely. This is part of their simplicity and their power. Transcendental functions like e raised to x require infinite data to specify exactly, either as infinite series, or as solutions to differential equations, or as limits. We can approximate them with polynomials, but the full function escapes finite description. Yet in practice, finite approximations suffice. We never need infinite precision. 15 digits of e raised to e is more than enough for any physical application. The diameter of the observable universe is only about 10 to the 60 times the Planck length. 15 digits of e raised to e exceeds any precision relevant to physics. So the distinction between finite and infinite, between polynomial and transcendental, matters philosophically and mathematically, but not always practically. We live in a finite world, computationally and physically, and polynomials suffice for everything we actually do. This is why numerical methods work. We replace infinite processes with finite approximations, and the approximations are good enough. Error bounds tell us how good, how many terms we need, how much we can trust the result. Consider Monte Carlo methods, which use randomness to approximate integrals or solve problems. You generate random points, evaluate the function, average the results. By the law of large numbers, the average converges to the integral, to the true value, as the number of points increases. This is a different kind of approximation. Not polynomial, not series-based, but statistical. Yet it works, often efficiently, for problems where other methods struggle. In high dimensions, where the curse of dimensionality makes grid-based methods infeasible, Monte Carlo shines. Random sampling doesn't care about dimension. 1,000,000 random points is 1,000,000 random points whether the space is 3-dimensional or 3,000-dimensional. But for our purposes, thinking about e raised to e, one-dimensional functions, polynomials and series, are the natural tools. We sum terms, truncate when accuracy suffices, and get numerical values we can work with. The psychology of large numbers is worth considering. We understand small numbers intuitively. 5 apples, 10 people, $100, but 1,000,000, a billion? These are just words labels for quantities beyond direct perception. E raised to e is about 15. That's still graspable. E raised to e is about 3. That's big, but not unimaginable. A city might have 1,000,000 people. 3,000,000 is 3 such cities. E raised to e is approximately 10 to the 6 millionth power. This number is so large it defies comprehension. It has over 6 million digits. If you wrote a digit per second, it would take months to write. If you used 1 atom per digit, you'd need more atoms than exist in observable galaxies. At this scale, numbers cease to have direct meaning. They become abstract tokens, symbols we manipulate, but not quantities we understand viscerally. This is where mathematics departs from experience, where we need formalism to guide us, because intuition fails. Yet the formalism works. The rules of arithmetic, the properties of exponentials, the convergence of series, all apply just as well to e raised to e as to 5 plus 3. The mathematics doesn't care about our psychological limitations. This is liberating and humbling. Liberating because we can reason about things far beyond experience. Humbling because we realize how limited our intuition is, how much we depend on tools and structures to extend our reach. Polynomials are one such tool. They let us compute, approximate, reason about functions we cannot directly grasp. They have a cognitive prosthesis that lets us do mathematics beyond mental arithmetic. In education, polynomials are often taught as just another topic. Quadratic formula, factoring, graphing parabolas. But there's so much more. They're the foundation of continuous mathematics, the bridge from algebra to analysis, the key to understanding how we compute anything. Recognizing this changes how we might teach them. Not as isolated techniques, but as part of a larger story about approximation, about representation, about how we make the complex tractable. The story we've been telling, from simple sums of powers to Taylor series to power towers of ease, illustrates this. Each step builds on the previous, each idea connects to others, the whole forming a web of understanding. And at the center of that web are polynomials, simple, foundational, indispensable. They're the reason we can do calculus. Without polynomials, we could define derivatives and integrals abstractly, but we couldn't compute them. We couldn't solve equations, model phenomena, make predictions. With polynomials, all of this becomes possible. We approximate smooth functions, integrate term by term, solve differential equations, fit data, compress information, encode signals. The applications are endless because polynomials are universal. So when we computed e raised to e, we were not just calculating a number. We were demonstrating the power of polynomial approximation, the universality of Taylor series, the way simple sums of powers can reach any function, any value, given enough terms. And we were exploring the edges of this universality. E raised to e grows so fast it challenges our methods. The Taylor series still works, but we need more terms, higher precision, careful error analysis. We're pushing polynomials to their limits, seeing where the approximation struggles and where it succeeds. This exploration is valuable in itself. Mathematics grows by finding limits, boundaries, edges. We push methods until they break, then develop new methods, Stronger tools, deeper theories. Polynomials lead to series, lead to complex analysis, lead to special functions, each stage expanding what we can express and compute. The journey never ends. There are always deeper questions, harder problems, richer structures to discover. E raised to E is one small station on an infinite line, interesting for what it teaches us, for the methods we develop to understand it, for the connections it reveals to other areas of mathematics. In the quietness of this exploration, patterns emerge. We see symmetry in the coefficients of series, order in the chaos of rapid growth, beauty in the relationships between seemingly unrelated concepts. This is why mathematicians work, not for applications, though those matter, but for the joy of discovery, the satisfaction of understanding, the aesthetic pleasure of elegant structures. Polynomials embody this elegance. They're simple enough to grasp completely, yet rich enough to support the entire edifice of modern mathematics. They're elementary in the best sense, fundamental elements from which everything else is built. And exponentials, particularly the base e, are their natural partners. Where polynomials are discrete, finite sums of powers, exponentials are continuous growth, infinite in their reach. Together they span the space between algebra and analysis, between the countable and the continuous. Our exploration of e raised to e has been an exploration of this partnership, how polynomials approximate exponentials, how compositions of exponentials create super-exponential growth, how series converge despite the rapid increase, how we compute with infinite sums that we truncate to finite ones. And through it all, the mathematics remains coherent, consistent, beautiful. The definitions hold, the theorems apply, the calculations work. We can trust the process because the foundations are solid, the logic sound, the structure carefully built over centuries of mathematical thought. This trust is what allows us to work with confidence in realms far beyond direct experience. We know e raised to e is unimaginably large, but we also know we can compute it, bound it, relate it to other quantities, understand its properties. The mathematics gives us purchase on the infinite, the tools to grapple with the abstract. And at the heart of those tools are polynomials, those simple sums of powers, proving once more that they're not just a topic in algebra, but the secret foundation of all continuous mathematics, the key that unlocks everything else, the reason we can do what we do. This is the gift they offer, and understanding it deepens our appreciation, not just of polynomials, but of mathematics itself, of how simple rules generate infinite complexity, of how finite minds can grasp truths beyond imagination, of how beauty and utility intertwine in structures we discover and create. Looking at the landscape we've mapped so far, where polynomials serve as our foundation, and exponentials reveal depths, we can only glimpse through infinite processes. We arrive now at questions of structure itself. What happens when we step back from individual functions, and ask about the spaces they inhabit, the transformations that connect them, the patterns that emerge when we view mathematics not as isolated objects, but as vast interconnected territories? Consider the real number line. Every point represents a number, but more than that, every number represents a potential input to any function we might imagine. The line extends infinitely in both directions, dense with rational numbers, yet mostly filled with irrationals, those numbers that cannot be expressed as fractions, whose decimal expansions never repeat. Between any two real numbers, no matter how close, infinitely many other real numbers nestle. This density means the real line has no gaps in a certain sense, yet it's also riddled with structure. The rationals are countable, meaning we could theoretically list them all, while the reals are uncountable, a larger infinity. Most real numbers are transcendental, not roots of any polynomial equation with rational coefficients. The exponential function e raised to x maps this real line to the positive half of itself. Every real input produces a positive real output. 0 maps to 1. Positive inputs map to numbers greater than 1. Negative inputs map to numbers between 0 and 1. The function is continuous, smooth, always increasing, never bending back on itself. This mapping has interesting properties. It's injective, meaning different inputs always give different outputs. It's surjective onto the positive reals, meaning every positive number is the exponential of some real number. Together, these properties make e raised to x a bijection from all reals to positive reals, a perfect one-to-one correspondence. The inverse function, the natural logarithm, maps positive reals back to all reals. The composition of a function with its inverse gives the identity, e raised to the natural log of x equals x, for positive x. the natural log of e raised to x equals x, for all real x. These identities express the fundamental relationship between exponential and logarithm, two sides of the same coin. Now think about what happens when we compose exponentials with themselves. The function e raised to x is no longer a simple bijection. It maps reals to positive reals, but not surjectively. The smallest value it achieves, when x approaches negative infinity, is 0 as a limit, but never actually 0. When x equals negative infinity in a limiting sense, e raised to x approaches 0. So e raised to x approaches e raised to 0 equals 1. Actually, let me reconsider. As x decreases toward negative infinity, e raised to x decreases toward 0. So e raised to x decreases toward e raised to 0 equals 1. But it approaches from above. The function never actually reaches 1 for any finite x. When x equals 0, e raised to x equals 1. So e raised to x equals 1. So e raised to x equals e. As action crosses function grows without bound, faster than any exponential of x itself. This super-exponential growth is characteristic of iterated exponentials. Each nesting multiplies the growth rate. E raised to x grows exponentially. E raised to x grows exponentially in the exponent, which means it grows faster than any polynomial power of e raised to x. E raised to x would grow faster still, and so on. These towers, exponentials, appear in combinatorics, in the sizes of certain finite structures, and the complexity of algorithms. They represent growth so rapid it's almost incomprehensible. The difference between e raised to 100 and e raised to 100 is unimaginably vast, far larger than the difference between 100 and e raised to 100. Yet we can still analyze these functions using the tools we've developed. Series expansions work locally. Near any point where we want to approximate, differential equations might capture their behavior implicitly, even if we can't solve them explicitly. Numerical methods let us compute values to any desired precision. The interplay between symbolic and numeric understanding runs throughout mathematics. Symbolically, we manipulate expressions, proving theorems, deriving identities, understanding relationships. Numerically, we compute specific values, solve equations approximately, visualize behavior. Neither approach alone suffices. Together they give us leverage. Returning to polynomials, consider them not just as individual functions, but as elements of a vector space. The set of all polynomials of degree, at most, n forms a vector space of dimension n plus 1. The basis for this space consists of 1, x squared, up to x to the n. Any polynomial in the space can be written uniquely, as a linear combination of these basis elements. Linear combinations mean we can add polynomials, and multiply them by constants. Adding two polynomials adds their coefficients. Multiplying a polynomial by a constant multiplies all coefficients by that constant. These operations satisfy the axioms of a vector space. There's a zero element. Addition is computative and associative. Scalar multiplication is compatible with field multiplication, and so on. This vector space structure is not just formal. It gives us tools. We can talk about dimension, about bases, about linear transformations. Differentiation is a linear transformation from the space of polynomials of degree at most n to the space of polynomials of degree at most n minus 1. It takes a vector space to another vector space, respecting the linear structure. Similarly, integration is a linear transformation, though it increases degree. Multiplying by x is a linear transformation that also increases degree. These transformations can be composed, inverted when possible, studied using linear algebra. The matrix representation of a linear transformation depends on a choice of basis. In the standard basis of 1, x squared, differentiation is represented by a matrix that's mostly zeros, with the diagonal just above the main diagonal containing the values 1, 2, 3, and so on. This matrix acts on the coefficient vector, transforming a polynomial to its derivative. Understanding transformations through matrices connects calculus to linear algebra. The eigenvalues and eigenvectors of a transformation tell us about invariant directions, about how the transformation stretches or rotates or reflects the space. For differentiation on polynomials, the only eigenvector is 0, since differentiation always reduces degree for non-zero polynomials. But if we extend our space to include all formal power series, infinite sums of the form sum of a(n) times x to the n, then exponentials become eigenvectors. The series for e raised to lambda x is an eigenvector with eigenvalue lambda. The series for sine and cosine become eigenvectors of the second derivative, with eigenvalues -1. This extension from finite-dimensional polynomial spaces to infinite-dimensional function spaces is both natural and subtle. Many concepts from finite dimensions carry over: bases, linear combinations, transformations. But new phenomena appear. Convergence matters. Not all formal sums represent functions. Topology enters. The study of closeness and limits, and continuity. In finite dimensions, all norms are equivalent. Two different ways of measuring the size of a vector give rise to the same notion of convergence. In infinite dimensions, this fails. The space of continuous functions on an interval has multiple natural norms, and they're not equivalent. Some sequences converge in one norm, but not another. The space of square integrable functions, those whose squared magnitude integrates to a finite value, forms a Hilbert space. This is an infinite-dimensional vector space, with an inner product, the way of measuring angles and lengths. The inner product of two functions, f and g, is the integral of f times the complex conjugate of g. In this space we can talk about orthogonal functions, those whose inner product is 0. Sines and cosines of different frequencies are orthogonal in this sense. So are Legendre polynomials, Hermite polynomials, Laguerre polynomials, all the orthogonal polynomial families that appear in mathematical physics. Orthogonal functions are useful for the same reason. Orthogonal vectors are useful in finite dimensions. They provide independent directions. Expanding a function as a sum of orthogonal functions is like expressing a vector in terms of orthogonal basis vectors. The coefficients can be computed independently using inner products. Fourier series expand periodic functions as sums of sines and cosines. The coefficients are the inner products of the function with each sine or cosine. Since the sines and cosines are orthogonal, these coefficients capture independent information about the function. Together they reconstruct the function, at least in the limit. For smooth periodic functions, Fourier series converge quickly. For functions with discontinuities, the series converge more slowly and exhibit Gibbs' phenomenon, an overshoot near jumps that never quite goes away. For functions that aren't even square integrable, the series might not converge at all in the usual sense. These convergence questions are subtle and important. When we say a series equals a function, we need to specify what kind of convergence we mean. Pointwise convergence means at each point, the series converges to the function value. Uniform convergence means the convergence is equally good at all points simultaneously. Convergence means the integral of the squared difference goes to 0. Different notions of convergence are appropriate for different purposes. Uniform convergence preserves continuity. If a sequence of continuous functions converges uniformly, the limit is continuous. Pointwise convergence doesn't have this property. A sequence of continuous functions can converge pointwise to a discontinuous function. For Fourier series, convergence in mean is guaranteed for square integrable functions. Pointwise convergence is guaranteed at points where the function is smooth. Uniform convergence happens for continuously differentiable periodic functions. These results, the theorems of Fourier analysis, specify precisely when and how Fourier series represent functions. The exponential function, being smooth and periodic in the complex plane, with period 2 pi I, has well-behaved Fourier series when restricted to any horizontal strip. The series converge rapidly, allowing accurate approximation with few terms. But e raised to x is not periodic, even in the complex plane. It has more complicated behavior. We cannot expand it as a Fourier series in the usual sense. We need other tools, other series, other approximation methods. One approach is to use Taylor series near specific points. Near x equals 0, we've discussed the series. Near x equals 1, we could expand in powers of x minus 1, getting different coefficients but the same function. Each Taylor series has a radius of convergence, a region where it represents the function accurately. For entire functions like e raised to x, functions analytic everywhere in the complex plane. A Taylor series around any point converges everywhere. But the rate of convergence varies. Far from the expansion point, more terms are needed for a given accuracy. Another approach is asymptotic expansion. Instead of trying to represent the function exactly, we find a series that approximates it in a limiting regime. For e raised to x, as x goes to infinity, we can derive an asymptotic series in powers of 1 over x, or more accurately in powers of 1 over e raised to x. These asymptotic series often diverge. The terms decrease at first, but eventually grow without bound. Yet they're useful. If we truncate at the smallest term, we get an approximation that's extremely accurate, better than any convergent series might provide with comparable effort. This seems paradoxical. How can a divergent series be useful? The answer lies in understanding what the series represents. It's not claiming the infinite sum equals the function. It's claiming that for large x, the function minus the first n terms of the series is smaller than the n plus first term, in a specific technical sense. This is good enough for many purposes. We can compute the function to high accuracy using just a few terms. The fact that including more terms eventually makes things worse doesn't matter if we stop at the optimal truncation point. Asymptotics is the art of understanding behavior and limits. As x goes to infinity, as a parameter goes to 0, as a dimension increases, functions exhibit characteristic behaviors. Capturing these behaviors with simple expressions, even if those expressions are only approximations, gives insight and computational power. For e raised to x, the dominant behavior as x increases is clear. The function grows like e raised to x, which is to say it is what it is. We can't simplify it to something more elementary, but we can understand how rapidly it grows, how it compares to other functions. What happens if we perturb it slightly? Perturbation theory, the study of how solutions change when we slightly modify problem, is central to applied mathematics. Often we can solve a simplified problem exactly, but only approximately solve the real problem. Perturbation methods let us use the simple solution as a starting point, correcting it systematically. For differential equations, perturbation methods expand the solution as a series in a small parameter. The zero-order term solves the simplified equation. The first-order term corrects for the perturbation. Higher-order terms refine the correction. If the series converges, we get the exact solution. If it diverges, we still get useful asymptotic information. The exponential function appears constantly in perturbation theory because it solves linear constant coefficient equations exactly. We perturb around exponential solutions, finding corrections that account for nonlinearity, variable coefficients, inhomogeneities. Nested exponentials like e raised to x appear in nonlinear problems where the perturbation itself involves exponentials. Certain models of population growth, where the growth rate depends exponentially on the population, lead to such equations. The solutions exhibit rapid transitions, sharp thresholds, behaviors that linear models cannot capture. These nonlinear phenomena are among the richest areas of modern mathematics. Chaos theory, bifurcation theory, dynamical systems, all study what happens when linearity breaks down. Small changes in initial conditions can lead to large changes in outcomes. Systems can transition suddenly from one behavior to another. Simple equations can produce incredibly complex dynamics. The logistic map, defined by x goes to r times x times 1 minus x, is a simple quadratic but exhibits chaos for certain values of r. Iterating the map, feeding the output back as the next input, produces sequences that appear random, despite being deterministic. This sensitivity to initial conditions, this unpredictability from simple rules, is characteristic of chaos. Maps x goes to r times e raised to x, or variations, also exhibit chaos. The iteration of exponentials is less studied than polynomials, but no less rich. The Julius sets and Fatou sets, regions of different dynamical behavior in the complex plane, have fractal structure for exponential maps, just as they do for polynomial maps. Fractals, sets with self-similar structure at all scales, appear throughout mathematics. The Mandelbrot set, defined by iterating z, goes to z squared plus c, and asking whether the orbit stays bounded, is perhaps the most famous. Its boundary is fractal, infinitely detailed, never smoothing out, no matter how much we zoom in. For exponential maps, similar sets exist. They're harder to compute because exponentials grow faster than polynomials, causing numerical overflow more easily. But mathematically, they're just as well defined, just as beautiful, just as complex. Complexity here means more than just complicated. It means exhibiting structure at all scales, having dimension that's not an integer, possessing statistical properties that remain consistent under magnification. Fractals are complex in the measurable, quantifiable sense. The dimension of a fractal, the Hausdorff dimension, can be a non-integer value between the topological dimension and the dimension of the space containing it. A fractal curve in the plane might have dimension 1.5, meaning it's more than a line but less than an area. This fractional dimension reflects how much space the set occupies in a scaling sense. Computing Hausdorff dimension rigorously is difficult. Often we use box counting dimension, covering the set with boxes of size epsilon, and seeing how the number of boxes scales as epsilon decreases. if the number of scales like epsilon to the negative d, and d is the dimension. For the boundary of the Mandelbrot set, the dimension is believed to be 2, the same as the plane, though this hasn't been rigorously proven. For other fractals, like the Cantor set or Sierpinski triangle, we can compute dimensions exactly. The Cantor set has dimension natural log of 2 over natural log of 3, about 0.63. These fractal sets connect to exponentials through dynamics. The stable and unstable manifolds of hyperbolic fixed points in dynamical systems are often fractal. The basin boundaries separating different behaviors are fractal. Exponentials, with their rapid growth, create the nonlinearity needed for this complexity to emerge. Let's shift perspective again and think about functions as objects we can manipulate, transform, combine in various ways. We've discussed composition, nesting functions inside each other. We've discussed arithmetic, adding and multiplying functions. We've discussed differentiation and integration, calculus operations that transform functions to related functions. Another operation is convolution, blending two functions together in a specific way. The convolution of f and g is defined as the integral of f of t times g of x minus t over all t. This creates a new function that smooths both inputs, capturing their combined effect. Convolution appears in probability, where the sum of independent random variables has a probability density that's the convolution of the individual densities. It appears in signal processing, where a system's output is the convolution of the input with the system's impulse response. It appears in differential equations, where convolution with a Green's function solves inhomogeneous equations. The Fourier transform converts convolution to pointwise multiplication. The Fourier transform of a convolution is the product of the Fourier transforms. This property makes Fourier methods powerful for solving problems involving convolution. Transform both functions, multiply, transform back. The Fourier transform itself is an integral transform, taking a function to a new function that encodes the same information in a different way. The transform of f is the integral of f of t times e raised to negative I omega t over all t, where omega is the frequency variable. This transform decomposes f into its frequency components. Each value of omega corresponds to a pure oscillation at that frequency. The transform value in omega tells us how much of that frequency is present in f. For a pure sine or cosine at frequency omega 0, the transform is concentrated at omega equals omega 0, and omega equals negative omega 0. The exponential function e raised to negative I omega t is the key to this decomposition. It's a complex exponential, combining cosine and sine via Euler's formula. Its magnitude is 1, so it doesn't amplify or attenuate. Its phase rotates at a constant rate determined by omega. Multiplying f by this exponential, and integrating effectively, picks out the component of f that oscillates at frequency omega. Components at other frequencies average to 0 due to orthogonality. Components at the same frequency reinforce. The inverse Fourier transform reconstructs f from its transform. The formulas are symmetric, differing only in the sign of the exponent and normalization constants. This symmetry reflects a deep duality between time and frequency, position and momentum, space and wave number. In quantum mechanics, the position wave function and momentum wave function are Fourier transforms of each other. Measuring one destroys information about the other, a manifestation of the uncertainty principle. The product of position uncertainty and momentum uncertainty is bounded below by Planck's constant. This uncertainty is not due to measurement imperfection. It's fundamental, built into the mathematics of wave functions and operators. The position operator and momentum operator do not commute. Their commutator is a constant times the identity. This algebraic relation encodes the uncertainty principle. Exponentials appear here too, as eigenfunctions of the momentum operator. The wave function e raised to ikx is an eigenfunction with eigenvalue k. It represents a particle with definite momentum, completely uncertain position, since the magnitude of the wave function is constant everywhere. Conversely, a delta function, infinitely narrow and infinitely tall, represents a particle with definite position, but completely uncertain momentum. Its Fourier transform is constant, containing all frequencies equally. Real particles are described by wave packets, localized in both position and momentum, to the extent allowed by uncertainty. A Gaussian wave packet minimizes the uncertainty product, saturating the bound. Its position and momentum distributions are both Gaussian, related by Fourier transform. The time evolution of a wave packet is governed by the Schrödinger equation, a differential equation with the Hamiltonian operator. For a free particle, The Hamiltonian is the kinetic energy, proportional to the square of the momentum operator, which is minus the second spatial derivative. Solving the Schrödinger equation for a free particle is straightforward in momentum space. Each momentum component evolves independently, accumulating a phase proportional to the energy. In position space, this corresponds to the wave packet spreading out over time, while maintaining its center of mass motion. For a particle in a potential, the Hamiltonian includes both kinetic and potential energy. The eigenfunctions are no longer simple exponentials. For the harmonic oscillator, they're Hermite polynomials times Gaussians. For the hydrogen atom, they're products of spherical harmonics and Laguerre polynomials times exponentials. These special functions, solutions to differential equations with physical significance, form orthogonal bases for the relevant function spaces. We expand arbitrary wave functions in these bases, reducing the dynamics to evolution of coefficients. The connection between differential equations and orthogonal polynomials is deep. The Hermann equation, Laguerre equation, all have polynomial solutions for specific parameter values. These polynomials satisfy orthogonality relations with respect to weight functions, Gaussians for Hermite, constant for Legendre, exponentials for Laguerre. The weight functions make the differential equations self-adjoint, ensuring real eigenvalues and orthogonal eigenfunctions. Self-adjoint operators are the analog of symmetric matrices, having nice spectral properties, decomposing spaces into orthogonal eigenspaces. For the function e raised to x, there's no simple differential equation it satisfies. It's not an eigenfunction of any standard operator. It's not associated with an orthogonal polynomial family. It exists as a composition, built from simpler pieces, but not reducible to them in any elementary way. This irreducibility is common. Most functions are not special. They don't satisfy simple equations, don't have simple transforms, don't decompose nicely. We study them anyway, using approximation, using numerical methods, using whatever tools apply. The space of all continuous functions is vast beyond comprehension. The space of functions we can write down explicitly, using standard notation and operations, is infinitesimally small in comparison. Yet it contains remarkable richness, enough to occupy mathematicians indefinitely. Consider now the operation of taking limits, central to calculus and analysis. A sequence converges to a limit, if, beyond some point, all terms are arbitrarily close to the limit value. A function approaches a limit, as x approaches some value if the function values get arbitrarily close to the limit, when x is sufficiently close. Limits formalize the intuitive notion of approaching something. They make rigorous the idea of continuity, of smoothness, of all the calculus concepts we use. Without limits, we cannot define derivatives or integrals precisely. Without them, we cannot discuss convergence of series or solutions of like equations. The epsilon delta definition of a limit captures this precisely. We say the limit of f of x as x approaches a equals L. If for every epsilon greater than 0, there exists a delta greater than 0, such that whenever 0 is less than the absolute value of x minus a, which is less than delta, we have the absolute value of f of x minus L is less than epsilon. This definition is technical, but it's necessary for rigor. It says that by making x close enough to a, we can make f of x as close to L as we want. The challenge is that how close x needs to be depends on how close we want f of x to be, captured by delta depending on epsilon. For simple functions like polynomials, proving limits using this definition is straightforward. For more complex functions, it can be difficult. But once we establish basic properties, like the limit of a sum being the sum of limits, we can build up to complex cases without returning to first principles each time. The exponential function e raised to x is continuous everywhere, meaning the limit as x approaches any point equals the function value at that point. This continuity extends to the complex plane. E raised to z is entire, analytic everywhere, infinitely differentiable. The function e raised to x, is also continuous everywhere on the real line, and entire in the complex plane. Compositions of continuous functions are continuous. Compositions of analytic functions are analytic. The properties propagate, but consider the function that equals e raised to x, for rational x, and equals 0, for irrational x. This function is discontinuous everywhere. At every point, there are nearby rationals and irrationals, so the function jumps. Yet it's well defined, the legitimate function from reals to reals. Such pathological functions, discontinuous everywhere, challenge our intuition. They can't be graphed in any meaningful sense. they can't be integrated in the usual Riemann sense. They're not the functions we encounter in applications, but they exist, and understanding them clarifies the boundaries of our concepts. The Dirichlet function, 1 on rationals and 0 on irrationals, is the classic example. It's measurable and Lebesgue integrable, integrating to grading, since the rationals have measure 0. But it's not Riemann integrable, because upper and lower sums don't converge to the same value. Lebesgue integration extends Riemann integration by changing what we consider measurable. Instead of partitioning the domain into intervals, we partition the range into values and measure the preimages. This allows integration of functions that are too discontinuous for Riemann. Measure theory, the foundation of modern integration, assigns sizes to sets in a way that extends length, area, volume. Not all sets are measurable, at least not if we want measure to have reasonable properties. But the measurable sets include all sets we can construct without exotic set theoretic tricks. On the measurable sets, we could define integration as expected value in probability, as area under curves in geometry, as averages in analysis. The integral becomes a flexible tool, applicable far beyond its original context of computing areas. The exponential function, being continuous, is certainly measurable at any integrable over any finite interval. An integral of e raised to x from a to b equals e raised to b minus e raised to a. Over the entire real line, the integral diverges, being infinite in one direction. For e raised to e raised to x, the integral over any finite interval exists, and could be approximated numerically. The integral from -infinity to 0 is finite, since the integrand approaches 1, as x approaches -infinity, and decays quickly for moderately negative x. The integral from 0 to infinity diverges, since the integrand grows faster than any exponential. These integral properties connect to probability distributions. A function can be a probability density that is non-negative, and integrates to 1. The exponential distribution, with density lambda times e raised to negative lambda x for x greater than 0, is a standard probability model for waiting times. The double exponential, or Laplace distribution, with density 1/2 times lambda times e raised to negative lambda times the absolute value of x, is symmetric, and has heavier tails than the Gaussian. It models data with occasional large deviations. A distribution based on e raised to x would have extremely heavy tails, concentrating most mass near the mode, but having probabilities that decay doubly exponentially, rather than exponentially. Such distributions appear in extreme value theory, modeling the maximum of many samples. The Gumbel distribution, used for maxima, has cumulative distribution function, e raised to negative e raised to negative x. Its density is e raised to negative x times e raised to negative e raised to negative x, involving both the exponential and its composition. This appearance of nested exponentials in probability is not coincidental. Extreme values, rare events, tail behavior, all push us beyond simple exponential decay into regimes where iterated exponentials dominate. Risk analysis, reliability engineering, climate modeling, all deal with extremes. What's the probability of a flood exceeding a certain level? What's the expected lifetime of a system with multiple failure modes? Questions like these require distributions that capture tail behavior accurately. The mathematics of rare events is subtle. Small changes in assumptions can lead to large changes in predictions. Extrapolating from observed data to unobserved extremes is fraught with uncertainty. Yet decisions must be made, designs must account for worst cases, risks must be managed. Exponential functions, being the canonical model for decay and growth, serve as baselines. Deviations from exponential behavior signal different mechanisms, different physics, different underlying processes. A faster than exponential decay might indicate a finite time singularity. A slower than exponential growth might indicate saturation effects. The logistic function, 1 divided by 1 plus e raised to negative x, transitions smoothly from 0 to 1. Model in saturation. Its derivative is the logistic function times 1 minus the logistic function. The simple equation that leads to the logistic differential equation for population growth. This equation, di over dx equals r times y times 1 minus y over k, says the growth rate is proportional to both the population and the remaining capacity. When y is small, growth is exponential. As y approaches the carrying capacity, k, growth slows and eventually stops. The solution is a logistic curve, starting near 0, growing exponentially, then saturating near k. The inflection point, where growth is fastest, occurs at half the carrying capacity. This S-shaped curve appears in countless applications, from biology to economics to technology adoption. The logistic function is related to the hyperbolic tangent, another sigmoid function. Both are special cases of squashing functions used in neural networks, transforming arbitrary inputs into a bounded range. Neural networks, inspired by biological neurons, consist of layers of simple computational units. Each unit computes a weighted sum of inputs, applies a nonlinear activation function, passes the result to the next layer. Training adjusts the weights to minimize error on a dataset. The universal approximation theorem states that a neural network with a single hidden layer can approximate any continuous function arbitrarily well, given enough units. This is a powerful existence result, but doesn't tell us how to find the weights, or how many units are needed. In practice, deep networks with many layers often perform better than shallow networks, capturing hierarchical structure and data. The composition of many simple nonlinearities to represent complex functions compactually. Exponential functions appear in neural networks through the softmax function, which converts a vector of scores into probabilities. The probability of class I is e raised to the score I, divided by the sum of e raised to score j over all classes j. This ensures probabilities are positive, and sum to 1. The exponential amplifies differences between scores, making the highest score dominate. This is useful for classification, selecting the most likely class, but can lead to overconfidence. The cross-entropy loss function, used for training classification networks, involves the logarithm of predicted probabilities. Minimizing cross-entropy encourages the network to assign high probability to correct classes. The gradient of this loss with respect to the scores has a particularly simple form when using softmax. These connections between exponentials, logarithms, probabilities, and optimization are fundamental to modern machine learning. Gradient descent, the algorithm for training networks, follows the negative gradient of the loss function, taking steps in parameter space to reduce error. The gradient itself involves derivatives, that propagated through the network, using the chain rule. Each layer's contribution to the gradient depends on the derivatives of its activation functions. Exponentials, with derivatives equal to themselves, have particularly simple gradients. Deep networks can suffer from vanishing or exploding gradients. If derivatives are small, gradients diminish exponentially with depth, making early layers train slowly. If derivatives are large, gradients explode, causing instability. Careful initialization and architecture design mitigate these issues. Skip connections, allowing signals to bypass layers, help gradients flow. Normalization, rescaling activations to have mean 0 and variance 1, stabilizes training. Residual networks, building deep architectures from blocks with skip. Connections can be trained to hundreds or thousands of layers. These engineering solutions to mathematical challenges show how theory and practice inform each other. The mathematics of optimization, gradients, convergence, provides insight. Empirical experiments reveal which techniques work. Together they push capabilities forward. Returning to the function e raised to x from this perspective, we might ask whether it appears in neural networks or machine learning. Not prominently, but the principle of composition, building complex functions from simple ones, is central. Each layer of a network is a composition. The overall function computed by a deep network is a composition of compositions. An iterated transformation. While individual layers typically don't use nested exponentials, the overall architecture embodies the idea that iteration creates complexity. In recurrent neural networks, which process sequences, the same transformation is applied repeatedly, at each time step. The hidden state evolves according to a recurrence relation, similar to iterating a function. If the transformation involves exponentials, the iterated effect can resemble nested exponentials. Long short-term memory networks, a type of recurrent network, use gating mechanisms involving sigmoids and hyperbolic tangents to control information flow. These functions, related to exponentials, modulate what information is remembered or forgotten at each step. The dynamics of these networks, especially over long sequences, can be complex. Information can be stored, retrieved, transformed in intricate ways. The space of possible computations is vast, limited mainly by the number of parameters and training data available. Training these networks involves optimizing over a high-dimensional parameter space, often millions or billions of dimensions. The loss landscape, the surface defined by loss as a function of parameters, is incredibly complex, full of local minima, saddle points, plateaus. Yet gradient descent works surprisingly well in practice. The high dimensionality helps, providing many directions to move. Stochasticity, using random subsets of data for each update, adds noise that can escape shallow minima. Momentum, accumulating gradient information over time, accelerates convergence. The success of deep learning, training these complex models to perform tasks that seemed impossible a decade ago, is one of the great empirical achievements of recent mathematics and computer science. The theory lies behind practice in many ways. We know these methods work, but don't fully understand why. This gap between empirical success and theoretical understanding is not unique to machine learning. It appears throughout applied mathematics, physics, engineering. We use methods that work, refining them through experience, even when rigorous justification is lacking. Eventually, theory catches up, providing explanations, generalizations, guarantees. The development of mathematics has always involved this interplay between concrete problems and abstract theory, neither proceeding independently, each informing and motivating the other. The exponential function, from its origins in compound interest and population growth, has become central to vast areas of mathematics. It appears in calculus as the function that's its own derivative, in complex analysis as the function that's periodic in the imaginary direction, in linear algebra as the matrix exponential connecting continuous and discrete systems, in probability as the basis for countless distributions, in differential equations as the fundamental solution to constant coefficient equations. Nested exponentials extend this ubiquity to more specialized contexts. They model faster than exponential growth in combinatorics, complexity theory, and nonlinear dynamics. They appear in solutions to certain transcendental equations, in asymptotic expansions of special functions, in the analysis of algorithms. Understanding these functions requires tools from multiple areas of mathematics: series expansions from analysis, polynomial approximations from numerical methods, differential equations from applied mathematics, complex variable techniques from complex analysis. Each lens reveals different aspects, different properties, different applications. The journey from simple exponentials to nested exponentials to general compositions illustrates how mathematics builds complexity from simplicity, how iteration and combination create richness from basic building blocks. This is the essence of mathematical thinking. Start with simple objects, well understood and tractable. Combine them, transform them, study the results. When the results are simple, understand them completely. When they're complex, develop tools to analyze them approximately, asymptotically, numerically. Always there's the tension between exact and approximate, between symbolic and numeric, between finite and infinite. We want exact answers, but often approximate ones suffice. We want symbolic expressions, but numerical values might be all we need. We imagine infinite processes, but we compute with finite steps. Mathematics mediates these tensions, providing frameworks for rigor, while accommodating approximation, enabling symbolic manipulation while grounding it in computation, defining infinite objects, while relating them to finite constructions. The exponential function, in all its forms, exemplifies this mediation. It's defined as a limit, an infinite series, but we compute it with finite sums. It's an exact solution to differential equations, but we often approximate those solutions numerically. It's a transcendental function, beyond algebra, but we understand it through polynomial approximations. The studying e raised to x. We're not just studying one peculiar function. We're exploring how mathematics handles complexity, how tools developed for simple cases extend to harder ones, how rigorous theory and practical computation work together. The function is simple to write, two symbols and a variable, but its behavior is rich. Its analysis requires sophisticated tools. Its properties connect to deep areas of mathematics. This is typical. Simple expressions can have complex implications. The challenge and joy of mathematics lie in unraveling these implications, discovering what's hidden in what seems obvious, finding structure in apparent chaos.